Hello there, and welcome to Science for Sleep, where curiosity settles in gently and the universe unfolds at a pace that does not demand anything from you. Tonight, we are drifting far beyond our own familiar spiral of stars, far beyond the quiet glow of the Milky Way, toward a galaxy with a name that sounds more like a catalogue number than a cosmic wonder. UGC 12,591. Not exactly poetic. Not the sort of name you would whisper while looking up at the night sky. And yet, behind that unassuming label lies something extraordinary. This is a galaxy that spins so quickly, so confidently, that by all ordinary expectations it should not be holding itself together at all. Imagine for a moment standing on the edge of a vast carousel. The faster it spins, the harder it becomes to stay upright. Spin it even faster, and eventually, anything not firmly anchored will fly outward. That seems intuitive. That seems reasonable. And galaxies in many ways behave like enormous cosmic carousels. Billions of stars orbiting a shared centre, held in place by gravity. The faster they move, the stronger that inward pull must be to keep them from drifting away into the dark. Now consider this gentle question. Where are you listening from tonight? Is it late where you are, or just beginning to grow quiet? Perhaps you're curled up under a blanket, or maybe you're watching the ceiling while the world outside slows down. And what time is it in your corner of the Earth? It feels fitting to ask, because the galaxy we're about to explore measures time in rotations that take hundreds of millions of years. One orbit around its centre is longer than all of human history combined. So wherever you are, and whenever this finds you, you are sharing a moment that is brief beyond measure on the scale we are about to discuss. If you find this kind of journey calming, or even just gently interesting, I would be very grateful if you liked the video and perhaps subscribed. It helps this quiet little space reach others who might need something steady and thoughtful at the end of a long day. And now, let us ease into the story of a galaxy that should not exist the way it does. UGC 12,591 resides roughly 400 million light-years away from us, in the direction of the constellation Coma Berenices. That distance alone is almost too large to grasp. The light we see from it tonight began travelling toward Earth long before dinosaurs disappeared. It left when Earth looked entirely different, and yet, after crossing unimaginable distances, it arrives here and quietly enters the lenses of telescopes. At first glance, UGC 12,591 does not look wildly different from other spiral galaxies. It has a central bulge, it has arms, it has structure. It is by classification a spiral galaxy. But numbers tell a different story. When astronomers measured how fast this galaxy rotates, they discovered something startling. Most spiral galaxies rotate at speeds of around 200 to 300 kilometers per second at their outer regions. Our own Milky Way, for example, rotates at about 220 kilometers per second at the Sun's position. That is already astonishingly fast. At that speed, you could circle Earth in just over 2 minutes, and yet UGC 12,591 rotates at over 500 kilometers per second in its outer regions. 500. That is not a small difference. That is not a rounding error. That is nearly double the typical speed. Now here is where things become puzzling. According to Newton's understanding of gravity, the faster something moves in orbit, the stronger the gravitational pull must be to keep it from escaping. If a galaxy spins that quickly, its gravity must be immense, and gravity, in a galaxy, comes primarily from mass, stars, gas, dust, visible matter. So astronomers did what astronomers always do. They began estimating the galaxy's mass. They counted its stars. They measured its brightness. They analysed the gas. They added everything up. And what they found did not fully explain the speed. If UGC 12,591 contained only the visible matter we can see, it should not be able to spin that fast without flying apart. Its outer stars should drift away. Its spiral arms should unravel. And yet, they do not. the galaxy remains intact, rotating steadily, calmly, as if unaware that it is defying expectations. At this point, you might feel a gentle shift in the story, because when gravity seems insufficient, astronomers tend to reach for something that has become both familiar and mysterious over the past century: dark matter. Before we wander too deeply into that invisible territory, let us slow down and understand why this situation is so surprising. Imagine a spinning ice skater. When she pulls her arms inward, she spins faster. That is conservation of angular momentum. The mass is concentrated closer to the center, so rotation increases. In galaxies, stars orbit the center due to gravity. The farther out you go, the weaker gravity should become if most mass is concentrated near the center. That means outer stars should orbit more slowly. That is what we would expect. But beginning in the 1970s, astronomers like Vera Rubin discovered that galaxies do not behave this way. Their outer regions rotate much faster than visible matter alone would allow. Instead of declining speeds, rotation curves remain flat, sometimes even rising slightly. UGC 12591 takes this already surprising pattern and pushes it further. It is not merely fast, it is one of the fastest rotating spiral galaxies ever observed. It stretches the limits of what we consider typical. This galaxy contains around 1 trillion stars. That alone is immense. The Milky Way contains perhaps 100 to 400 billion stars. UGC 12591 may contain more than twice that number. It is larger, more massive, and more extended than our own galaxy. But even that abundance of stars does not fully account for its rotation speed. Which brings us gently back to gravity. Gravity is not just a force pulling Apple downward or planets inward. It is the fundamental glue of large-scale structure in the universe. Without gravity, stars would not form, galaxies would not coalesce, clusters would not gather, everything would drift apart. Yet gravity depends on mass, and mass, at least the kind we can see, appears insufficient in many galaxies. So astronomers propose that galaxies are embedded in vast halos of unseen matter. Dark matter does not emit light, it does not absorb light, it does not reflect light, it interacts primarily through gravity. If UGC 12591 possesses an enormous halo of dark matter, that could explain its astonishing rotation. In fact, measurements suggest that the total mass of this galaxy, including dark matter, may approach several trillion times the mass of the Sun. To put that in perspective, imagine weighing something you cannot see by watching how everything around it moves. That is exactly what astronomers do. They measure velocities, they trace rotation curves, they analyze the gravitational influence on surrounding gas, and from those movements, they infer mass. UGC 12591 appears to be wrapped in one of the most massive dark matter halos known for a spiral galaxy, and yet it remains a spiral. There is another quiet surprise here. Galaxies that grow extremely massive often lose their spiral structure. They collide, merge, and eventually become elliptical galaxies. Spirals are delicate in some sense. Their structure can be disrupted by violent interactions. UGC 12591, however, seems to have grown large while maintaining its spiral form. That suggests a relatively calm history. Fewer catastrophic mergers, a steady accumulation of matter rather than chaotic collisions. How does something grow so enormous and still remain organized? That question carries us deeper into the life stories of galaxies. Galaxies are not static objects. They evolve. They merge. They accrete gas from intergalactic space. They form new stars. They experience bursts of activity and long, quiet phases. In the early universe, matter was distributed more evenly. Over time, gravity pulled it into denser regions. Dark matter collapsed first, forming scaffolding. Baryonic matter, the normal matter that makes up stars and gas followed into these gravitational wells. If UGC 12591 formed within an especially massive dark matter halo early on, it would have had access to enormous reservoirs of gas. That gas could cool and form stars over billions of years, building a vast stellar disk. Its rotation speed then becomes a natural outcome of the deep gravitational well it inhabits. And still, there is something subtly dramatic about the idea of a galaxy spinning at over 500 kilometers per second, calmly, steadily, for billions of years. It is not chaotic. It is not tearing itself apart. It is simply balanced. That balance is delicate. Centrifugal force pulling outward due to rotation, gravity pulling inward due to mass. When those forces are in equilibrium, structure persists. Perhaps that is part of what makes galaxies so quietly compelling. They are not just collections of stars, they are systems in balance. Vast rotating ecosystems of matter and motion. If you were somehow able to stand in the outer disk of UGC 12591, which is not possible but imagine it gently, you would not feel that speed directly. You would orbit along with everything else. The stars around you would appear relatively stable. The motion becomes noticeable only when compared to the center. That is another curious aspect of rotation. Motion can feel still when everything moves together. Now, as we move forward, we will explore how astronomers measure such velocities in the first place. We will look at the tools, the spectral lines, the Doppler shifts that reveal motion across cosmic distances. Because none of this comes from guesswork. It comes from light stretched and shifted across space. But before we do, pause for a moment and consider the scale again. 400 million light-years away, a trillion stars, a rotation speed over 500 kilometers per second. A dark matter halo possibly several trillion solar masses in size. All of that, turning quietly in the dark. There is something steady about that image, something grounding. A reminder that even in a universe that expands and evolves, there are systems that find equilibrium and maintain it for billions of years. And in that sense, UGC 12591 is not just a curiosity, it is a laboratory. A test case for our understanding of gravity, dark matter, and galactic formation. It challenges our models not by breaking them completely, but by pushing them to their limits. How do you measure the spin of something so far away? How do you weigh a galaxy whose mass is largely invisible? When astronomers talk about UGC 12591, they're referring to a single object, but the name itself hints at something important about how it was first known. UGC stands for the Uppsala General Catalogue, a large survey compiled in the 20th century to list galaxies visible from the Northern Hemisphere. The number attached to it is not a nickname, not a poetic title, and not an attempt to capture its character. It is simply an entry in a long list, and for a long time, that is all it was. One more spiral galaxy recorded, classified and set aside among tens of thousands of others. Yet within that quiet catalogue entry lives one of the most extreme spiral galaxies ever observed. UGC 12591 is what astronomers would describe as a massive spiral galaxy, but even that phrase does not fully communicate its scale. Spiral galaxies come in a wide range of sizes. Some are small and faint, with loosely defined arms and modest stellar populations. Others, like the Milky Way, sit comfortably in the middle of the distribution, large enough to host hundreds of billions of stars while still maintaining a graceful structure. UGC 12591 sits far out toward the upper end of that range. Its stellar disk stretches across hundreds of thousands of light-years. Its total number of stars is estimated to be close to 1 trillion. Its mass, when dark matter is included, is among the highest known for any spiral galaxy. This is not a system that barely qualifies as large. It is enormous by any reasonable standard. Despite that, it does not draw immediate attention in the night sky. You cannot see it without powerful telescopes. It does not blaze with intense star formation or flare with dramatic jets. It exists quietly, rotating steadily, far away in intergalactic space. This contrast between its immense scale and its subdued presence is part of what makes it so intriguing. To understand what kind of galaxy UGC 12591 is, it helps to first consider how astronomers classify galaxies in general. Galaxies are grouped based on their appearance, structure, and stellar content. Spiral galaxies are flattened disks, central bulges, and arms that curve outward. Elliptical galaxies are more rounded or elongated, lacking clear disks or arms. Irregular galaxies have no obvious shape. UGC 12591 is a spiral galaxy, but it is not a fragile one. Its disk is thick and massive. Its central bulge is prominent. The spiral arms are present but not especially bright, suggesting that star formation is relatively subdued compared to more active spirals. This galaxy is not in the middle of a dramatic growth spurt. It is not burning through gas at a furious rate. It appears mature. That maturity tells us something about its history. Galaxies form and evolve over billions of years. Early in the universe, they were smaller and more chaotic. Over time, through the slow pull of gravity, they gathered mass. Some grew by merging with others. Some grew by steadily drawing in gas from their surroundings. UGC 12591 appears to belong to the second category. Its structure suggests that it did not experience too many violent mergers in its recent past. Large mergers tend to disrupt spiral structure. They scramble stellar orbits and often result in elliptical galaxies. The fact that UGC 12591 remains a spiral implies a relatively calm evolutionary path, at least in the later stages of its life. This raises an interesting point. How does a galaxy grow so massive without destroying its own structure? The answer likely lies in the environment it inhabits. Galaxies do not exist in isolation. They are part of a larger cosmic web, a vast network of filaments and voids formed by dark matter. Along these filaments, gas flows slowly inward toward gravitational centers. A galaxy embedded in a particularly massive dark matter halo can quietly collect this gas over billions of years. That slow, steady inflow allows the galaxy to grow without the chaos of major collisions. Stars form gradually. The disk remains stable. The galaxy becomes larger, heavier, and faster spinning, all while preserving its basic shape. UGC 12591 seems to be an example of this process taken to an extreme. It sits in a region of space that is not especially crowded. It is not at the center of a dense cluster where gravitational interactions are frequent and violent. Instead, it appears relatively isolated. That isolation may have protected it from disruptive encounters while allowing it to quietly accumulate mass. Now, let us talk more directly about the darkness that surrounds it, because the phrase quiet darkness is not just a metaphor. Most of the mass associated with UGC 12591 does not shine. It does not glow. It does not announce itself. Dark matter makes up the majority of the galaxy's mass. Without it, the visible stars and gas would not be enough to explain the galaxy's rotation speed. Without it, the disk would not be stable. Without it, UGC 12591 would likely not exist in its current form. Dark matter is called dark, not because it is black or shadowy, but because it does not interact with light. It does not emit radiation. It does not absorb photons. Telescopes cannot see it directly. Instead, its presence is inferred through gravity. In the case of UGC 12591, that gravitational influence is unmistakable. The outer stars move far too quickly to be held in orbit by visible matter alone. Something else must be contributing to the gravitational pull. That something is dark matter. The dark matter halo surrounding UGC 12591 is thought to be enormous, extending far beyond the visible disk. This halo is roughly spherical. enveloping the galaxy like an invisible cocoon. Within it, the galaxy stars orbit, their motions guided by a gravitational field dominated by something they cannot see. It is worth pausing here to appreciate just how strange that is. 1 trillion stars, each one burning nuclear fuel, each one visible across vast distances, are collectively outweighed by something completely invisible. The luminous part of the galaxy is not the main contributor to its gravitational identity. That realization has reshaped astronomy over the past several decades. It has forced scientists to rethink how galaxies form, how they evolve, and how structure emerges in the universe. UGC 12591 is an especially clear example of this imbalance between light and mass. Another defining feature of this galaxy is its rotational behavior. We have already mentioned that it spins faster than any other known spiral galaxy. But what does that actually mean in practical terms? Rotation in galaxies is measured by observing the Doppler shift of light emitted by stars and gas. When part of the galaxy moves toward us, its light is shifted slightly toward shorter wavelengths. When it moves away, the light shifts toward longer wavelengths. By measuring these shifts across the disk, astronomers can map out how fast different regions are moving. In UGC 12591, those measurements revealed astonishing speeds. The outer disk rotates at more than 500 km per second. That speed is sustained over a large radius, indicating that the gravitational pull remains strong far from the centre. This behaviour is not random. It reflects the underlying mass distribution. A massive dark matter halo produces a gravitational field that does not weaken as quickly with distance as visible matter alone would. As a result, stars remain bound even at extreme speeds. It is tempting to think of this galaxy as somehow breaking the rules, but in reality it is highlighting the rules we do not fully understand. The laws of gravity still apply. What is uncertain is the precise nature and distribution of the mass involved. UGC 12591 also challenges assumptions about the upper limits of spiral galaxies. For a long time, astronomers believed there was a practical ceiling on how massive a spiral galaxy could be. Beyond a certain point, it was thought that disks would become unstable, or mergers would dominate growth. This galaxy suggests that under the right conditions, spirals can grow larger and faster than previously expected. That does not mean such galaxies are common. UGC 12591 appears to be rare. But rarity does not diminish significance. In fact, it often increases it. Outliers are valuable because they test the boundaries of our theories. They reveal where models work well and where they begin to strain. UGC 12591 sits right at that boundary. Another subtle aspect of this galaxy is its star formation rate. Despite its size and mass, it is not producing stars at an unusually high rate. This suggests that it may have already converted much of its available gas into stars, or that conditions within the disk are not especially favourable for new star formation. This calm behaviour fits with the idea of a mature system. The most intense periods of star formation likely occurred billions of years ago. What we see today is the result of long-term stability rather than ongoing upheaval. The central region of UGC 12591 likely contains a supermassive black hole, as most large galaxies do. While we do not yet have precise measurements of its mass, it is reasonable to assume that it scales with the galaxy's size. Even so, the black hole would account for only a tiny fraction of the total mass. Its influence is important locally, but it does not drive the galaxy's overall rotation. That role belongs to the dark matter halo. When you step back and consider all of this together, a picture begins to form. UGC 12591 is not a chaotic anomaly. It is not a galaxy on the verge of destruction. It is a highly organized, massive system that has found a stable balance between rotation and gravity. Its quietness is deceptive. Beneath that calm exterior lies extreme motion and enormous mass. It is spinning faster than almost any other spiral galaxy, yet doing so with remarkable composure. There is something deeply instructive about that. Extreme conditions do not always announce themselves with fireworks. Sometimes they persist quietly, revealing their nature only through careful measurement and patient observation. How astronomers first realized that this galaxy was unusual? What drew attention to it? What measurements tipped researchers off that something extraordinary was happening? Long before UGC 12591 earned its quiet reputation as one of the fastest rotating spiral galaxies ever measured, it was simply another entry in observational surveys, another distant smudge of light catalogued and archived. Large sky surveys produce enormous amounts of data. Thousands upon thousands of galaxies are recorded, classified, and stored in databases. Most of them follow familiar patterns. Their brightness aligns with expectations. Their rotation speeds fall within known ranges. Their structures match established models. Nothing particularly dramatic stands out. And then, occasionally, a set of numbers does not behave. The moment astronomers noticed something unusual about UGC 12591 did not involve a sudden flash or a dramatic image splashed across a telescope monitor. It began with spectroscopy. Light from the galaxy was analysed in detail, split into its component wavelengths to examine how its stars and gas were moving. This is a routine process in astronomy. Telescopes collect light. Instruments measure how that light is shifted by motion. From those shifts, velocities are calculated. When a galaxy rotates, one side moves slightly toward us, and the other side moves slightly away. This produces a measurable difference in wavelength known as the Doppler effect. By mapping these shifts across the disk, astronomers can construct what is called a rotation curve, a graph showing how orbital speed changes with distance from the centre. For most spiral galaxies, the shape of this curve is familiar. Speeds rise rapidly near the centre, where gravity is strongest, and then flatten out in the outer regions. The flattening itself was once surprising, as it implied the presence of dark matter. But over the decades, flat rotation curves became expected. UGC 12591 did not simply flatten, it soared. When researchers examined the velocity data, they saw outer regions moving at speeds exceeding 500 km per second. That number alone required a second look. In astronomy, extraordinary measurements are not accepted casually. Instrument calibration is checked. Data reduction methods are reviewed. Possible contamination from nearby sources is ruled out. Observers verify that the spectral lines being measured truly belong to the galaxy in question. It is easy to imagine the quiet focus in that moment. A graph displayed on a computer screen. Data points extending higher than anticipated. No fireworks, no dramatic music. Just a number that did not sit comfortably within expectations. At first, it might have seemed like an error. High rotation speeds can sometimes be misinterpreted if the galaxy's inclination is misjudged. The tilt of a galaxy relative to our line of sight affects how we measure its motion. If a galaxy is not oriented exactly edge-on, corrections must be applied. A small mistake in estimating the angle can significantly alter derived velocities, so astronomers re-evaluated the inclination. They studied the shape of the disk. They examined imaging data. They recalculated the corrections. The numbers remained high. Next came mass estimates based on luminosity. A galaxy's brightness provides clues about how many stars it contains. From that, astronomers can estimate the mass of visible matter. These calculations suggested that UGC 12591 was indeed massive, but even its impressive stellar population did not fully account for the extreme rotation speed. Again, checks were performed. Was there an unusually bright bulge skewing the results? Was star formation contributing additional light? Were there foreground objects affecting the measurement? The results held steady. At that stage, what had initially appeared as a statistical outlier began to take shape as something more significant. UGC 12591 was not merely a large spiral galaxy, it was one of the fastest rotating spiral galaxies ever observed. Now, in scientific research, unusual results do not instantly become discoveries, they undergo scrutiny. Independent teams analyse similar data. Additional observations are requested when possible. Radio telescopes may be used to trace neutral hydrogen gas in the outer disk. Optical telescopes examine stellar populations. X-ray observatories search for signs of hot gas that might contribute to mass. In the case of UGC 12591, multiple lines of evidence converged. Its rotation curve remained steep and high even at large radii. The galaxy's mass, when inferred from gravitational effects, far exceeded what visible matter alone could explain. This was not entirely unprecedented. Other galaxies had hinted at similar discrepancies, but UGC 12591 pushed the upper limit further than most. There is a subtle difference between confirming a theory and stretching it. Dark matter had already become an accepted component of galactic models. Flat rotation curves were not new. What made this galaxy noteworthy was the scale of the effect. The implied dark matter halo had to be extraordinarily massive. The realization carried both excitement and caution. On one hand, the existence of such a galaxy reinforced the dark matter framework. It provided another example where invisible mass explained observed motion. On the other hand, it prompted questions about how such a massive halo could form around a spiral galaxy without disrupting its structure. Observational astronomy often advances through these quiet inflection points. A measurement appears routine, data is processed, a graph looks slightly unusual, a calculation is repeated. Gradually, the unusual becomes undeniable. One can imagine the tone of internal discussions at the time, not dramatic declarations but measured statements. This velocity seems high. Let's verify the inclination. Run the mass-to-light ratio again. Science moves deliberately, especially when confronting results that challenge expectations. As additional analysis confirmed the numbers, UGC 12591 began to shift from catalogue entry to case study. Its rotation speed placed it in a category few spiral galaxies occupied. It forced astronomers to examine how far the relationship between mass and rotation could extend. There is a well-known empirical relation in astronomy called the Tully-Fisher relation. This relationship connects a spiral galaxy's luminosity to its rotation speed. In simple terms, brighter galaxies tend to rotate faster. It has been used for decades to estimate distances and study galaxy evolution. UGC 12591 appeared to sit at the extreme end of that relation. Its luminosity was high, and its rotation speed was higher still. While it did not break the relation entirely, it occupied a region near the boundary of what was commonly observed. That boundary is where theory becomes especially attentive. The day astronomers noticed something unusual was not marked by headlines. It was marked by careful confirmation. Numbers were checked, assumptions were tested, instrumental biases were ruled out. Only after this process did the significance become clear. What made the discovery particularly compelling was that the galaxy did not show signs of being disturbed or in transition. It was not in the middle of a merger. It did not display chaotic asymmetries. It was stable, symmetrical, ordered. This stability suggested that its extreme rotation was not temporary. It was not the result of a recent collision or gravitational interaction. It was intrinsic to the galaxy's structure. That realization opened the door to deeper questions. How common are such massive spiral galaxies? Are they rare outliers, or have surveys simply not identified enough of them yet? What conditions in the early universe would allow such a system to form and persist? There is also something quietly humbling about the way discoveries like this unfold. A galaxy 400 million light-years away, spinning at over 500 kilometers per second, existed long before human beings built telescopes. It rotated steadily through epochs of cosmic history, and only recently did we notice that its motion was exceptional. It did not change when we measured it. It did not adjust its speed to match our models. It simply continued its rotation, indifferent to whether it fit neatly into theoretical expectations. The unusual aspect was not in the galaxy's behaviour, it was in our awareness. Astronomy is full of such moments. A star that dims unexpectedly, a galaxy that rotates too quickly, a background signal that does not match predictions. Each time the process is similar. Observe, measure, question, confirm, interpret. UGC 12591 joined that list, not because it contradicted physics, but because it expanded the known range of galactic behaviour. As more surveys scanned the sky, astronomers began looking more carefully for similarly extreme systems. They refined their models of dark matter halos. They adjusted simulations of galaxy formation to account for the possibility of very massive, stable, spiral galaxies. The discovery also underscored the importance of large statistical samples. Without broad surveys cataloguing thousands of galaxies, it would be difficult to identify outliers. Patterns become clear only when enough data points exist to define a norm. UGC 12591 emerged from that statistical background as a clear deviation. There is something fitting about the quiet nature of this realization. No sudden explosion, no dramatic flare, just a persistent set of data that refused to align with expectations. What does it mean for a galaxy to approach the upper limits of rotational stability? How much mass is required to maintain such motion without tearing apart the disk? Numbers, when written on a screen, can feel calm and harmless. 500 kilometers per second does not look dramatic in text. It is tidy, contained, easy to read, and yet when astronomers first confirmed that UGC 12591's outer disk rotates at well over 500 kilometers per second, the natural question was not simply, "That is fast." The real question was more precise. How fast is too fast? To answer that, we need to move carefully through what spin actually means for a galaxy. A spiral galaxy is not a rigid object like a solid wheel. It is a vast gravitational system made up of stars, gas, dust, and dark matter. Each star orbits the centre under the influence of gravity. The disk rotates because billions of these individual orbits align into an organised structure. Measuring that rotation requires patience and technique. Astronomers cannot watch a galaxy spin in real time. One full rotation for a star in the outer disk can take hundreds of millions of years. Instead, they infer motion through the Doppler effect. Light carries information. When an object moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, it shifts toward the red. This effect is subtle but measurable. By mapping these shifts across a galaxy's disk, astronomers reconstruct how fast different regions are moving. Imagine drawing a line across the diameter of a spiral galaxy. On one side, the stars are moving slightly toward us. On the other side, they are moving slightly away. The difference between those shifts reveals the rotation speed. The larger the shift, the higher the velocity. In UGC 12591, those spectral shifts are pronounced. Even after correcting for distance and inclination, the velocities remain extreme. But before accepting any measurement, astronomers must account for geometry. Galaxies are rarely oriented perfectly edge-on to our line of sight. Most are tilted at some angle. That tilt affects how much of the true velocity we observe. If a galaxy were face-on, we would see almost no Doppler shift at all, because motion would be mostly sideways relative to us. If it were edge-on, the Doppler effect would be maximized. So researchers estimate the galaxy's inclination by studying its apparent shape. A perfectly circular disk appears elliptical when tilted. By measuring that ellipticity, they infer the angle. That angle is then used to correct the observed velocities to determine the true rotation speed. In the case of UGC 12591, inclination corrections were applied carefully. Even with conservative estimates, the rotation speed exceeded 500 kilometers per second. Now consider what that means in terms of gravity. For an object in orbit, centrifugal acceleration outward must be balanced by gravitational acceleration inward. If the outward force from rotation exceeds gravity, the object escapes. If gravity dominates, the orbit tightens. The relationship between orbital velocity and mass is described by a simple expression derived from Newtonian gravity. The square of the orbital velocity is proportional to the gravitational constant times the mass enclosed within that orbit, divided by the radius. In practical terms, higher velocity at a given radius requires more mass inside that radius. For typical spiral galaxies, outer disk velocities around 200 to 300 kilometers per second correspond to total masses of roughly 1 trillion solar masses, including dark matter. Doubling that velocity does not simply double the required mass. Because velocity enters the equation squared, a significant increase implies a dramatic rise in total mass. If UGC 12,591 rotates at over 500 kilometers per second at large radii, the mass enclosed within those radii must be enormous. Astronomers therefore construct rotation curves, plotting velocity against distance from the center. These curves tell a detailed story about mass distribution. In many galaxies, the curve rises quickly near the center and then flattens out. The flattening indicates the presence of extended dark matter halos. UGC 12,591's rotation curve does not just flatten at a moderate value, it stabilizes at an exceptionally high one. At this point, a deeper question emerges. Is there an upper limit to how fast a spiral galaxy can rotate while remaining stable? Galactic disks are delicate structures. Stars orbit in relatively thin planes. If rotation becomes too extreme without sufficient gravitational support, instabilities can develop. Spiral arms can become distorted. Bars can form. The disk can thicken or fragment. Computer simulations of galaxy formation suggest that there are practical constraints. As halos grow more massive, mergers become more likely. Major mergers often disrupt spiral structure and produce elliptical galaxies. Therefore, the most massive galaxies in the universe are typically ellipticals rather than spirals. UGC 12591 appears to challenge that pattern. It combines extreme mass and extreme rotation with preserved spiral structure. One possibility is that its growth was unusually smooth. Instead of experiencing violent mergers, it may have accreted matter gradually from surrounding filaments of the cosmic web. Smooth accretion allows the disk to maintain its integrity while growing larger and more massive. Another factor to consider is angular momentum. Galaxies acquire angular momentum through tidal interactions in the early universe. Regions of matter pull on each other gravitationally, imparting spin. The distribution of that angular momentum influences the final structure of the galaxy. If UGC 12,591 formed in an environment where angular momentum was particularly high and accretion was orderly, it could develop both mass and rotation without catastrophic disruption. Still, the numbers remain striking. 500 kilometers per second is not merely high, it approaches the escape velocities of some galactic systems. And yet, the stars remain bound. To appreciate the scale, consider our own Milky Way. The Sun orbits the center at about 220 kilometers per second. At that speed, it takes roughly 230 million years to complete one orbit. In UGC 12591, stars at comparable radii move more than twice as fast. Their orbital periods are shorter relative to distance, but the gravitational well is deeper. If you were to imagine a star in the outer disk of UGC 12,591, it would be moving through space at extraordinary speed. And yet, relative to its surroundings, the motion would feel steady. Everything in the disk shares that rotation. This leads to another subtle point. There is no universal threshold labelled too fast. The limit depends entirely on mass. A system can spin as quickly as its gravity allows. The true question is not about speed alone, but about the mass required to sustain it. In UGC 12,591, sustaining 500 km per second requires a dark matter halo with mass estimated at several trillion solar masses. That places it among the most massive halos known for spiral galaxies. But measuring mass indirectly introduces uncertainty. Dark matter cannot be seen. Its distribution must be inferred from rotation curves and other gravitational effects. Small changes in assumed halo shape or density profile can affect total mass estimates. Astronomers therefore compare multiple models. They test different halo profiles such as Navarro-Frank-White models derived from simulations. They examine how well each model reproduces the observed rotation curve. In UGC 12,591's case, the data consistently point toward a very massive halo. There is no easy way to reduce the velocity without reducing the mass, and there is no visible matter sufficient to explain the mass. As measurements accumulated, the question shifted from "is this correct?" to "what does this imply?" It implies that spiral galaxies can inhabit extraordinarily deep gravitational wells. It implies that dark matter halos can grow to immense sizes without necessarily transforming the galaxy into an elliptical form. It implies that the upper boundary of spiral galaxy mass may be higher than once thought. There is also the matter of stability over time. A galaxy rotating this quickly must have maintained equilibrium for billions of years. Any imbalance between outward centrifugal forces and inward gravity would lead to structural changes. Yet observations show no sign that UGC 12,591 is on the verge of tearing itself apart. Its disk remains intact. Its spiral structure persists. That stability reinforces the conclusion that its mass distribution is sufficient to counterbalance its rotation. At this stage, the phrase "defies gravity" becomes more nuanced. The galaxy does not violate gravitational laws. Instead, it appears to demand an extraordinary amount of gravity to remain bound. It pushes our intuition about how much mass a spiral galaxy can contain. As astronomers continue studying such systems, they refine simulations of galaxy formation. They explore whether similar high-velocity spirals exist, but have not yet been identified. They examine the relationship between halo mass and disk structure. And quietly, in the background, UGC 12,591 continues to rotate. What exactly holds those stars in orbit? How does gravity scale across such vast distances? And why does visible matter alone fail to account for the motion we observe? At first glance, the idea that a galaxy could fly apart does not feel intuitive. Galaxies look calm in photographs. Their arms curve gently. Their light appears smooth and orderly. Nothing about them suggests instability or imminent disintegration, and yet, when you reduce a galaxy to its basic ingredients, motion and gravity, the possibility becomes very real. A spiral galaxy is a rotating system. Rotation creates an outward tendency. Gravity pulls inward. The entire structure exists only because those two influences are balanced with remarkable precision. Remove too much gravity, and the stars drift outward. Increase rotation without adding mass, and the disk becomes unstable. The galaxy does not explode, but it slowly unravels, stars peeling away over cosmic timescales. This is not speculation. It follows directly from the same physical principles that govern planets, orbiting stars, and moons orbiting planets. The difference is scale. In a galaxy, the distances are vast, the mass is enormous, and the timescales almost incomprehensibly long. But the rules remain familiar. To understand why galaxies should fly apart under extreme rotation, it helps to start small. Imagine a stone tied to a string, swung in a circle. As the stone moves, it pulls outward on the string. The faster it moves, the stronger that pull becomes. The string provides the inward force that keeps the stone from flying away. If the string breaks, the stone moves off in a straight line. In this analogy, the stone is a star, the string is gravity, and the motion is orbital rotation. Gravity must be strong enough to constantly redirect the star's motion inward. If it is not, the star escapes. Now remove the string and replace it with something invisible. That is essentially what happens in a galaxy. There is no physical tether. Gravity alone provides the inward pull, and gravity weakens with distance. The farther a star is from the galactic centre, the weaker the gravitational attraction becomes, unless additional mass is present. In a simple system where most mass is concentrated near the centre, orbital speeds should decline with distance. That is what we see in planetary systems. Planets farther from the Sun move more slowly because gravity weakens with distance. If galaxies behaved the same way, their outer stars would orbit more slowly than inner ones. But observations show that this is not the case. Rotation speeds remain high far from the centre. In UGC 12,591, they remain exceptionally high. This is where the tension appears. High rotation speeds at large distances require strong gravity far from the centre. Strong gravity far from the centre requires mass spread throughout the galaxy, not just concentrated in its luminous core. Without that mass, the galaxy should not remain intact. Let us be clear about what flying apart would actually look like. Stars do not suddenly shoot outward in dramatic fashion. Instead, they slowly drift away, their orbits becoming unbound. Over hundreds of millions or billions of years, the disk thins, spiral arms lose coherence, the galaxy becomes diffuse. Eventually, it may resemble a loose cloud of stars rather than a well-defined structure. This gradual unravelling is precisely what gravity prevents. In UGC 12,591, the outward tendency created by rotation is extreme. At over 500 kilometers per second, the centrifugal effect is enormous. To counterbalance that effect, gravity must be equally strong across a large volume. Visible matter alone cannot provide that strength. The stars we see contribute gravity, but their distribution declines with distance. Gas adds some mass, but not nearly enough. Even accounting for all luminous components, there is a significant shortfall. This mismatch is not subtle. It is large enough that without additional mass, the outer disk should not be bound. That realization is what led astronomers, decades ago, to propose the existence of dark matter. Dark matter provides gravity without light. It can extend far beyond the visible edge of a galaxy, maintaining a strong gravitational field where luminous matter is scarce. In the case of UGC 12,591, the need for dark matter is especially pronounced. The galaxy's rotation speed implies a dark matter halo that dominates its gravitational profile, but before leaning too heavily on dark matter, it is worth examining whether gravity itself could behave differently on galactic scales. This question has motivated alternative theories, such as modifications to Newtonian dynamics. These ideas attempt to explain flat rotation curves without invoking unseen matter. However, regardless of theoretical preference, the basic problem remains the same. Something must provide the inward pull. Whether that something is dark matter or a modified law of gravity, the requirement is unavoidable. The phrase defies gravity can therefore be misleading if taken literally. UGC 12,591 does not ignore gravity. It demands a tremendous amount of it. This demand becomes clearer when we consider escape velocity. Escape velocity is the speed required for an object to break free from a gravitational field. For Earth, it is about 11 kilometers per second. For the Sun, it is about 618 kilometers per second at the surface. In galaxies, escape velocity varies with distance and mass distribution. If a star's orbital speed approaches or exceeds local escape velocity, it will not remain bound. In UGC 12,591, outer stars move at speeds that approach what would normally be considered extreme. Without a massive halo, those speeds would be sufficient to unbind them. The fact that they remain bound tells us that escape velocity in this galaxy is also high. That means the gravitational potential well is deep. A deep potential well does not arise by accident. It reflects a large total mass distributed over a wide region. Another way to think about this is energy balance. Orbital motion involves kinetic energy. Gravity provides potential energy. For a stable orbit, the total energy must be negative. If kinetic energy exceeds gravitational binding energy, the orbit becomes unbound. In UGC 12591, the kinetic energy of outer stars is very high. The only way to keep total energy negative is to increase gravitational binding energy. Again, that requires mass. This leads us to an important constraint. There is a practical upper limit to how fast a galaxy can spin for a given mass distribution. Exceed that limit, and stability is lost. So when astronomers ask, how fast is too fast? They're really asking, how much mass is required to sustain this speed? In typical spiral galaxies, the answer lies within a relatively narrow range. In UGC 12591, the answer stretches that range to its extreme. There is also the issue of disk stability beyond simple binding. Rapid rotation can amplify instabilities within the disk. Spiral arms are density waves. Bars can form through gravitational instabilities. Excessive rotation without sufficient vertical support can cause the disk to thicken. Yet observations suggest that UGC 12591's disk remains reasonably stable. It is thick but not chaotic. It does not show signs of imminent disruption. That stability implies not only sufficient mass, but also a well-distributed mass. A smooth, extended halo can provide stabilizing influence across the disk. This is one reason astronomers pay close attention to the shape of rotation curves. A rising or flat curve indicates mass distributed over a large radius. A declining curve suggests mass concentrated near the center. UGC 12591's curve remains high across its outer regions, pointing to a massive extended halo. At this point, it becomes clear why galaxies should fly apart under extreme rotation and why most do not. The balance between motion and gravity is delicate. Push rotation too high witut increasing mass, and the structure dissolves. Increase mass appropriately, and even extreme rotation can be sustained. UGC 12591 sits at that delicate boundary. It also serves as a reminder that intuition built from small-scale systems does not always scale cleanly to cosmic ones. In everyday experience, objects thrown fast enough escape. In galaxies, escape depends on vast invisible structures. Another subtle factor is time. Even if a galaxy was slightly unstable, the timescale for noticeable change could be billions of years. A system might appear stable now while slowly evolving. That possibility must always be considered. However, current observations do not suggest that UGC 12591 is in the process of disintegrating. Its structure appears well settled. That implies long-term stability. This stability strengthens the case that its gravitational framework is sufficient, not marginal. From a broader perspective, the fact that galaxies do not fly apart despite their rotation is one of the strongest pieces of evidence for dark matter. Without it, many galaxies would not hold together as observed. UGC 12591 simply makes that evidence harder to ignore. It also raises questions about the formation of such massive halos. How did so much dark matter accumulate around a single spiral galaxy? Was it an early overdensity in the cosmic web? Did its environment funnel matter efficiently into its halo? These questions tie gravity not just to present-day stability, but to cosmic history. As we move forward, the story naturally turns toward the unseen component itself. If gravity's tug is strong enough to counter extreme rotation, what exactly is providing that tug? How do we know it is there? And what does it tell us about the universe at large? By the time astronomers seriously considered dark matter as part of the explanation for UGC 12591, it was not a dramatic leap into speculation. It was a measured step taken because every visible option had already been weighed and found insufficient. The galaxy's stars, gas and dust had been accounted for. The geometry had been corrected, the instruments had been checked, and still the numbers refused to soften. Something unseen had to be contributing to the galaxy's gravity. Dark matter did not enter the picture for UGC 12,591 as a new idea invented on the spot. It arrived with decades of precedent behind it. Long before this galaxy was studied in detail, astronomers had already encountered a recurring problem across the universe. Galaxies rotated too fast. Clusters of galaxies moved as though they were heavier than they appeared. Gravitational lensing bent light more strongly than visible mass alone could explain. The concept of dark matter emerged not from a single mystery, but from many, all pointing in the same direction. In the 1930s, Fritz Zwicky studied the Coma cluster of galaxies and noticed that the galaxies within it were moving too quickly to be gravitationally bound by visible matter alone. He proposed the existence of unseen mass, which he called Dunkelmaterie. At the time, the idea was largely set aside, the data were limited. The implications were unsettling. Decades later, in the 1970s, astronomers like Vera Rubin provided compelling evidence by measuring the rotation curves of spiral galaxies. Her work showed that stars far from galactic centres were orbiting at nearly the same speeds as those closer in. According to Newtonian expectations, those outer stars should have been moving much more slowly. They were not. UGC 12,591 fits squarely into this lineage of discovery, but it amplifies the effect. Its rotation curve does not merely flatten at a modest velocity. It remains high, extraordinarily high, across a vast radius. This makes the presence of a massive dark matter halo not just plausible, but unavoidable. Dark matter, as it is currently understood, is not made of ordinary atoms. It does not form stars or planets. It does not emit or absorb electromagnetic radiation. Telescopes cannot see it directly. Its existence is inferred entirely through gravitational effects. That invisibility can make dark matter feel abstract, but its consequences are concrete. Without it, galaxies like UGC 12,591 would not remain bound. Their stars would drift outward. Their disks would thin. Over cosmic timescales, their structure would dissolve. The simplest way to visualize dark matter's role is to imagine it as a vast invisible halo surrounding the galaxy. This halo extends far beyond the visible disk, sometimes several times farther than the outermost stars. Within this halo, gravity remains strong even where luminous matter becomes sparse. In UGC 12,591, the halo must be especially massive and extensive. The galaxy's rotation speed demands it. Astronomers estimate the mass of dark matter halos by fitting models to observed rotation curves. These models describe how density changes with distance from the centre. One commonly used profile is the Navarro-Frank-White profile, derived from large cosmological simulations. It predicts a dense central region that gradually tapers off with distance. When applied to UGC 12,591, such models suggest a total mass of several trillion times that of the Sun. The visible stars contribute only a fraction of that total. The rest resides in the dark halo. This realization shifts how the galaxy is perceived. The luminous spiral arms, impressive as they are, become secondary features. The dominant structure is invisible. The galaxy's true size and mass are defined not by what we see, but by what we infer. There is something quietly profound about that shift. For most of human history, knowledge has been tied to sight. We trust what we can observe directly. Dark matter challenges that instinct. It forces us to accept that the universe is shaped by components that do not announce themselves with light. In the context of UGC 12,591, dark matter does more than solve a numerical problem. It explains how such a massive spiral galaxy can exist without tearing itself apart. It provides the gravitational glue that binds stars moving at extraordinary speeds. It also raises new questions. Why does this galaxy have such an unusually massive halo? Are there many others like it, or is UGC 12591 a rare outcome of specific conditions in the early universe? To approach those questions, astronomers look beyond individual galaxies and examine large-scale structure. Dark matter is thought to form a cosmic web, a network of filaments stretching across the universe. Galaxies form at the intersections of these filaments, where dark matter density is highest. If UGC 12591 formed at a particularly rich node in this web, it could have accumulated an exceptional amount of dark matter early on. That early advantage would shape its entire evolution. A deep gravitational well would attract gas efficiently. Star formation could proceed steadily over billions of years. The disk could grow large without suffering disruptive mergers. This scenario fits well with what we observe. UGC 12591 appears mature and stable. Its star formation rate is not extreme. Its structure is orderly. These features are consistent with long-term, relatively calm growth within a massive halo. Dark matter also plays a role in angular momentum. The distribution of dark matter influences how gas settles into a rotating disk. A massive halo can absorb angular momentum, allowing the disk to remain stable even as it spins rapidly. In this sense, dark matter is not merely passive mass, it actively shapes the dynamics of the visible galaxy. Despite its central importance, dark matter remains mysterious at a fundamental level. We do not yet know what particles compose it. Numerous candidates have been proposed, from weakly interacting massive particles to axions. Experiments on Earth and in space continue to search for direct evidence. UGC 12591 does not tell us what dark matter is made of, but it tells us something about what dark matter does. It builds deep gravitational wells. It stabilizes fast-rotating systems. It allows galaxies to exist in forms that visible matter alone could not support. Some researchers have explored alternative explanations, such as modified gravity theories, which adjust the laws of motion at very low accelerations. These theories aim to reproduce flat rotation curves without invoking dark matter. However, explaining a galaxy like UGC 12591 within such frameworks is challenging. The sheer scale of the required gravitational effect makes dark matter the more straightforward explanation. A modification that accounts for modest discrepancies may struggle to accommodate such extreme velocities without introducing additional complexity. That does not mean debate has ended. Science thrives on questioning assumptions. But in this case, UGC 12591 strengthens the case for dark matter by demonstrating how extreme the consequences of its absence would be. Another subtle aspect worth noting is that dark matter halos are not static. They grow over time through mergers and accretion. Smaller halos merge to form larger ones. This hierarchical growth is a cornerstone of modern cosmology. UGC 12591's halo may be the result of such a process carried out efficiently and early. If it avoided major late-time mergers, its disk could survive while its halo continued to grow. This possibility ties the galaxy's present-day rotation to events that occurred billions of years ago, when the universe was much younger and denser. There is a certain calmness in that connection. The extreme motion we measure today is the outcome of ancient processes unfolding over cosmic timescales. Nothing about UGC 12591 is hurried. Its speed is not frantic, it is sustained, balanced, and long-lived. As we settle into this understanding, the phrase dark matter enters the picture takes on a deeper meaning. It is not a sudden arrival. It is the gradual recognition that much of the universe operates beyond what we can see. For UGC 12591, dark matter is not an optional add-on. It is the framework within which everything else makes sense. How do you measure the mass of an invisible halo? How confident can we be in those estimates? What tools and assumptions are involved? There is something slightly unsettling about the idea of weighing an object that you cannot touch, cannot hold, and cannot even see in full. If someone handed you a stone and asked for its mass, you would place it on a scale. If someone pointed to a distant building, you might estimate its weight from its materials and structure. But when the object in question is a galaxy 400 million light-years away, composed mostly of invisible matter, the method must be different. And yet, astronomers weigh galaxies all the time. The process begins with motion. In the universe, motion is rarely random. Objects move because forces act on them, and on large scales the dominant force is gravity. Gravity does not announce itself with colour or texture. It reveals itself through acceleration. If you know how fast something is moving and how far it is from the centre of attraction, you can infer how much mass is pulling on it. This is the same reasoning that allowed scientists to measure the mass of Earth centuries ago. By observing the Moon's orbit, they could calculate Earth's gravitational influence. By observing planetary motion, they estimated the Sun's mass. The principle is simple. Orbital motion reflects gravitational pull, and gravitational pull reflects mass. With UGC 12,591, the same logic applies, but on a vastly larger scale. Astronomers first measure the galaxy's rotation curve, mapping how orbital velocity changes with distance from the centre. As described earlier, this is done using spectroscopy. Light from stars and gas is split into its component wavelengths, and the Doppler shifts reveal which regions are moving toward us and which are moving away. Once the true rotation speed at a given radius is determined, a straightforward gravitational equation can be applied. The mass enclosed within that radius is proportional to the square of the velocity, times the radius, divided by the gravitational constant. In simple terms, higher speed at a larger distance means more mass inside that orbit. For UGC 12,591, the outer regions rotated over 500 km per second at distances extending well beyond the bright central bulge. When those numbers are inserted into the gravitational relationship, the enclosed mass becomes enormous. But that is only the beginning, because the visible stars and gas contribute only part of that mass. Astronomers estimate visible mass by measuring luminosity. The brightness of a galaxy provides a rough measure of how many stars it contains. By applying a mass-to-light ratio, which depends on stellar population models, they can estimate how much mass resides in stars. Gas contributes additional mass, especially neutral hydrogen. Radio telescopes can detect the 21 centimetre emission line from hydrogen atoms, mapping gas distribution across the disk. That gas mass is added to the total visible matter. When this visible mass is compared to the mass required to sustain the observed rotation, a gap appears. In UGC 12,591, the gap is large. To account for the full rotation curve, astronomers must include a dark matter halo. But how do you weigh something invisible? The answer lies in fitting models to data. Dark matter halos are described using theoretical density profiles derived from cosmological simulations. One commonly used model is the Navarro-Frank-White profile, often abbreviated as NFW. This profile predicts how dark matter density decreases with distance from the centre of a halo. By adjusting the parameters of such a profile, astronomers can reproduce the observed rotation curve. The best-fitting model yields an estimate of total halo mass. For UGC 12,591, those fits indicate a halo mass of several trillion solar masses. This places it among the most massive halos known for spiral galaxies. There are, of course, uncertainties. Inclination must be estimated accurately. Distance must be known reliably. The shape of the halo may deviate from idealized models. Different density profiles can produce slightly different total masses. Astronomers address these uncertainties by exploring a range of plausible parameters. They test how sensitive the results are to changes in assumptions. They compare optical data with radio observations. They look for consistency across independent methods. Another technique used in weighing galaxies involves gravitational lensing. According to Einstein's general theory of relativity, mass bends space-time. Light travelling near a massive object follows curved paths. If a galaxy lies between us and a more distant background object, its mass can distort and magnify the background light. This effect provides an independent measure of mass distribution, including dark matter. For galaxies at UGC 12,591's distance, lensing is subtle, but can contribute to mass estimates when sufficient background sources are available. There is also X-ray emission from hot gas. In galaxy clusters, the temperature and distribution of hot intra-cluster gas provide clues about total gravitational mass. For individual spiral galaxies like UGC 12,591, X-ray measurements are more limited, but they can still constrain halo properties in some cases. Each method has strengths and limitations. Rotation curves provide detailed information about mass within the disk region. Lensing probes mass along the line of sight. X-rays trace hot gas in gravitational equilibrium. Together, they form a converging picture. Weighing UGC 12,591 is therefore not a single calculation, but a synthesis of observations. Spectral data reveal motion. Luminosity reveals visible mass. Models reveal dark matter distribution. The combination produces an estimate of total mass. What makes this process remarkable is that it does not require touching the galaxy. It relies entirely on light and physics. There is a quiet elegance in that approach. The galaxy rotates. Its light shifts slightly in wavelength. From that shift, velocity is calculated. From velocity and radius, mass is inferred. From mass and luminosity, dark matter is deduced. Step by step, the invisible becomes measurable. It is worth noting that this method assumes gravity behaves as described by Newton and Einstein on galactic scales. If gravity were fundamentally different at low accelerations, the interpretation might change. Some alternative theories attempt to explain rotation curves without dark matter by modifying gravitational laws. However, these alternatives must also account for lensing and large-scale structure formation. So far, dark matter remains the most consistent explanation across multiple lines of evidence. In the case of UGC 12,591, the inferred halo mass is so large that even alternative gravity theories would struggle to avoid invoking significant unseen mass or equivalent gravitational effects. Another aspect of weighing galaxies involves understanding their environment. Is UGC 12,591 part of a larger group? Does it interact with neighbouring galaxies? Environmental factors can influence halo growth and mass estimates. Current observations suggest that UGC 12,591 is relatively isolated. It is not embedded in a dense cluster where interactions dominate. That isolation makes its massive halo even more intriguing. It appears to have accumulated its mass without relying on cluster-scale dynamics. The idea of weighing something you cannot touch might feel abstract, but in practice, it is grounded in precise measurement and well-tested physical laws. When astronomers say UGC 12,591 has a mass of several trillion suns, that number is not a guess. It is the result of repeated observations, corrections, model fits and cross-checks. There is humility built into this process. Each assumption is tested, each uncertainty is acknowledged. The final number is usually presented with error bars, reflecting the range of plausible values. Still, even at the lower end of those ranges, UGC 12,591 remains extraordinarily massive. When astronomers talk about rotation curves, they're really talking about shapes. Not shapes you can see with your eyes, but shapes traced by numbers as distance increases. These curves are among the most quietly powerful tools in astrophysics because they translate motion into structure. They reveal how mass is arranged, even when most of that mass cannot be observed directly. A rotation curve is simple in concept. Along the horizontal axis, you place distance from the center of a galaxy. Along the vertical axis, you place orbital speed. Each point represents how fast stars or gas are moving at a particular radius. Connect those points, and a curve emerges. In a universe without dark matter, those curves would look very familiar. Near the center, where most of the mass resides, speeds would rise sharply. Then, as distance increases and enclosed mass stops growing significantly, speeds would decline. The curve would peak and then fall, much like the orbital speeds of planets in a solar system. That is not what astronomers see. In galaxy after galaxy, rotation curves refuse to fall. Instead, after rising near the center, they level off. Speeds remain roughly constant even far from the visible edge of the galaxy. This flatness is one of the strongest indicators that mass extends well beyond the luminous disk. UGC 12,591 follows this pattern, but with a striking difference. Its curve levels off at a much higher velocity than usual. To understand what this means, imagine tracing a curve that climbs steadily, and then settles into a plateau far above where you expected it to stop. That plateau is the signature of an extended, massive halo. The higher the plateau, the more mass is required to sustain it. In UGC 12,591, the plateau sits at over 500 kilometers per second. This tells us something specific about the galaxy's invisible structure. The dark matter halo must be both massive and extended. If the halo were compact, gravity would weaken rapidly with distance, and the curve would decline. If the halo were light, it would not support such high speeds. Instead, the curve implies a halo whose density decreases gradually, maintaining gravitational influence far beyond the visible disk. Rotation curves are not just diagnostic tools, they are maps of gravity. Each point on the curve corresponds to how much mass lies within that radius. By studying the curve's shape, astronomers can infer how mass is distributed throughout the galaxy. In UGC 12,591, the curve rises quickly near the center, indicating a dense core. That core includes the stellar bulge and inner disk. As distance increases, the curve does not drop. It remains high, indicating that mass continues to accumulate with radius. This accumulation cannot be explained by stars alone. The surface brightness of the galaxy declines with distance. Gas density drops as well. The luminous components thin out, yet the gravitational effect does not diminish accordingly. The only consistent explanation is that an invisible component dominates the outer regions. The shape of the rotation curve also provides clues about the halo's geometry. A smooth, symmetric curve suggests a relatively spherical halo. Strong asymmetries or irregularities might indicate disturbances or recent interactions. UGC 12,591's curve appears smooth and well-behaved. That supports the idea of a relaxed, stable halo rather than a chaotic or recently disturbed one. There is an important distinction to make here. Dark matter halos are not rigid shells. They are dynamic structures composed of countless particles interacting gravitationally. Over time, they can merge, grow, and evolve. But on the timescales relevant to galaxy rotation, they provide a stable gravitational background. The rotation curve effectively samples that background. Another subtle aspect of rotation curves is that they can reveal whether a galaxy's disk contributes significantly to its inner rotation. In some galaxies, the inner curve can be explained largely by visible matter. In others, dark matter dominates even near the center. In UGC 12,591, the inner regions show a strong contribution from stars, as expected given its massive bulge. But as radius increases, the dark matter contribution quickly becomes dominant. This transition point, where dark matter overtakes luminous matter in gravitational influence, occurs relatively close to the center compared to smaller spirals. that is consistent with an especially massive halo. The concept of an invisible halo might sound abstract, but the rotation curve makes it tangible. The halo's presence is written directly into the motion of stars and gas. It shapes their orbits continuously. One way to visualize this is to imagine walking outward from the galactic center while carrying a gravitational scale. At each step, you ask how much mass lies inside your orbit. In a galaxy like the Milky Way, that number rises steadily and then slows. In UGC 12,591, it keeps rising significantly. That continued rise is the halo. There is also a deeper implication hidden in the curve's shape. The fact that rotation curves are smooth suggests that dark matter is distributed smoothly on galactic scales. If dark matter were clumpy in the same way as stars, rotation curves would show bumps and irregularities corresponding to mass concentrations. Instead, they are remarkably smooth. This suggests that dark matter behaves differently from ordinary matter. It does not cool and collapse into dense clumps. It remains diffuse, forming extended halos rather than compact structures. UGC 12,591 reinforces this picture. Its extreme rotation requires not just a lot of dark matter, but dark matter arranged in a way that produces a stable gravitational field across a vast region. Rotation curves also help astronomers compare galaxies of different sizes and types. When plotted in normalized form, many spirals show similar curve shapes despite differences in mass. This universality hints at underlying principles governing halo formation. UGC 12,591 stands out because its curve is scaled up. The shape is familiar, but the amplitude is higher. This suggests that the same physical processes that form typical spiral galaxies can operate at larger scales under the right conditions. UGC 12,591 is not governed by entirely different rules. It is an extreme outcome of familiar ones. That insight matters. It means we do not need to invent new physics to explain its rotation. We need to understand how known processes can produce such massive systems. Another important feature of rotation curves is that they extend beyond the visible edge of the galaxy. Neutral hydrogen gas often reaches farther out than stars. By observing this gas in radio wavelengths, astronomers can trace rotation to even larger radii. In UGC 12,591, these extended measurements confirm that high velocities persist far into the halo-dominated region. This strengthens confidence in the inferred halo mass. Rotation curves also serve as inputs for simulations. By matching observed curves, simulations can test whether their assumptions about dark matter and galaxy formation are realistic. When simulations produce galaxies with rotation curves similar to UGC 12,591, they provide clues about the conditions required. These simulations often involve early formation of massive halos, efficient gas accretion, and relatively quiet merger histories. The curve becomes not just a measurement, but a constraint. There is a certain beauty in this indirect approach. We cannot see dark matter, we cannot touch it, but its gravitational fingerprint is unmistakable. It bends light, it shapes orbits, it leaves its mark in curves drawn from data. UGC 12,591's rotation curve is one of the clearest expressions of that fingerprint at extreme scale. It also invites a philosophical pause. Most of the galaxy's mass does not participate in the light we see. The visible spiral arms, impressive as they are tracers riding within a much larger invisible structure. The galaxy's true form is defined by what we cannot observe directly. This inversion of expectation is one of the defining features of modern cosmology. The universe is not dominated by what shines, it is dominated by what pulls. When astronomers describe UGC 12,591 as the fastest known spiral galaxy, the statement is not meant as a dramatic headline. It is a careful comparison based on measured rotation speeds across many observed systems. Spiral galaxies are common throughout the universe. They come in a wide range of sizes, brightness levels, and masses. Yet when their rotation curves are measured and placed side by side, UGC 12,591 consistently rises to the top of the distribution. The phrase "fastest known" requires precision. It does not mean that no faster spiral galaxy exists anywhere in the universe. It means that among those measured with sufficient detail and reliability, UGC 12,591 currently holds the record for rotational speed in its outer disk. That distinction matters. Astronomy is limited by what we can observe. Survey coverage, telescope sensitivity, and data quality all shape the catalogue of known galaxies. Still, within those limits, UGC 12,591 stands out clearly. To appreciate the scale of its rotation, it helps to look at typical values. In most spiral galaxies, outer disk speeds fall between 150 and 300 kilometers per second. Larger spirals, like the Milky Way, rotate at around 220 kilometers per second at the Sun's position. Even massive systems rarely exceed 350 or 400 kilometers per second. UGC 12,591 pushes past 500 kilometers per second. That difference is not marginal, because velocity enters gravitational equations squared. Increasing speed from 300 to 500 kilometers per second implies more than doubling the mass required to sustain the orbit at that radius. The leap in halo mass is substantial. In surveys of spiral galaxies, astronomers often examine relationships between luminosity and rotation speed. The Tully-Fisher relation connects a galaxy's brightness to how fast it spins. Brighter galaxies tend to rotate faster because they generally contain more mass. UGC 12,591 lies near the upper edge of this relation. Its luminosity is high, and its rotation speed is even higher. It does not completely violate the relation, but it stretches it to its extreme. In effect, it defines the upper boundary of what spiral galaxies appear capable of achieving. The fact that it remains a spiral is significant. Galaxies more massive than a few trillion solar masses often lose their disk structure and become elliptical systems. Ellipticals can contain far more stars than spirals, but their rotation patterns differ. Their stars move in more randomized orbits rather than organized disks. UGC 12,591 combines extreme mass with organized rotation. This combination makes it unusual. It suggests that the processes governing spiral galaxy formation can operate effectively even at very large scales, provided certain conditions are met. One of those conditions is a relatively calm merger history. Major mergers between galaxies can scramble disk structures. When two large spirals collide, the result is often an elliptical galaxy. The violent gravitational interactions disrupt ordered rotation. UGC 12,591 does not show strong signs of recent major mergers. Its disk appears intact. Its rotation curve is smooth. That implies that its growth likely occurred through gradual accretion of gas and smaller systems, rather than through catastrophic collisions. Being the fastest known spiral galaxy also means its dark matter halo is among the most massive for its class. Estimates place its total mass at several trillion times the mass of the Sun. Most of that mass resides in the halo, not in visible stars. This halo provides the gravitational anchor that allows such extreme rotation without structural failure. Another aspect to consider is stability. High rotation speeds can introduce instabilities within disks. Spiral arms can become distorted. Bars can form. Vertical thickness can increase. Yet UGC 12,591 appears relatively stable. That stability implies that its halo is not only massive but also well distributed. A smooth halo can help maintain equilibrium by providing consistent gravitational support across the disk. The record of fastest known is always provisional. Future surveys may uncover another spiral galaxy with even higher rotation speed. Large sky surveys continue to expand our catalogue of galaxies. Improved instrumentation increases precision. Radio observations extend rotation curves farther into the outer disk. But as of current measurements, UGC 12591 remains at the top of the known list. There is a quiet irony in this. The galaxy that rotates faster than any other measured spiral is not especially bright or flashy. It does not dominate the sky. It does not emit extraordinary jets or host dramatic starbursts. Its distinction lies in its motion. Motion is subtle when observed from such distance. We do not see stars streaking across space. We see faint shifts in spectral lines. From those shifts, the conclusion emerges. If you imagine standing at the outer edge of this galaxy, the speed would be astonishing by human standards. At 500 kilometers per second, you would circle Earth in less than a minute. But within the galaxy, everything shares that motion. It feels steady because it is consistent. The comparison with our own Milky Way provides context. If the Sun orbited at 500 kilometers per second instead of 220, the gravitational environment would be very different. The halo mass required would be far larger. The Milky Way would not look as it does today. UGC 12591 demonstrates that such massive, fast-rotating disks can exist without collapsing into elliptical forms. This challenges earlier assumptions that spiral galaxies have strict upper mass limits. Instead, it appears that under the right circumstances, spirals can grow to extraordinary sizes and speeds while preserving their structure. The rarity of such systems is important. UGC 12591 is not representative of the average spiral galaxy. It occupies the extreme tail of the distribution. Studying extreme cases is valuable because they test theoretical models. If models of galaxy formation cannot reproduce systems like UGC 12591, those models require refinement. Simulations must account for how such massive halos form and how disks survive within them. Modern cosmological simulations have begun to produce galaxies approaching these extremes, especially when initial conditions favour early halo growth and smooth accretion. This suggests that UGC 12591 is not impossible within current frameworks, but it is uncommon. The galaxy also raises questions about the early universe. Massive halos likely began forming early, when density fluctuations were larger. If UGC 12591's halo assembled quickly, it could have attracted gas efficiently before major mergers disrupted its disk. This early advantage would echo across billions of years, shaping its present-day rotation speed. Another subtle point is the role of angular momentum conservation. As gas falls into a dark matter halo, it retains angular momentum from its initial conditions. That angular momentum determines how the disk forms and how fast it rotates. If UGC 12591 began with unusually high angular momentum and a massive halo to anchor it, the result would be a large, fast-rotating disk. Being the fastest known spiral galaxy does not mean it is on the verge of instability. It means that it has found a balance at the extreme edge of parameter space. There is a difference between instability and extremity. UGC 12591 is extreme in speed and mass, but stable in structure. That distinction is critical. It suggests that the laws governing galaxy formation are robust across a wide range of scales. They can produce modest spirals like the Milky Way and giants like UGC 12591 without breaking. If one spiral galaxy can grow this large and spin this fast, could there be others even larger, perhaps beyond our current observational limits? Some galaxies are born small and remain modest for billions of years. Others begin with an advantage so slight it would be invisible to us at the time. Yet that early edge compounds steadily, patiently, until the result is something enormous. UGC 12591 appears to belong to the second category. Its present-day mass did not appear suddenly. It was assembled piece by piece over cosmic time. through processes that operate everywhere in the universe but rarely produce outcomes this extreme. To understand how a spiral galaxy becomes this massive without losing its structure, we need to go back to the beginning. Not to the formation of the galaxy itself, but to the formation of the scaffolding that allowed it to grow. Shortly after the Big Bang, the universe was remarkably uniform. Tiny fluctuations in density existed, slight overdensities and underdensities in the distribution of matter. These fluctuations were small, but gravity does not require dramatic differences to begin its work. Where matter was slightly denser, gravitational pull was slightly stronger. Over time, those regions attracted more matter. Growth began quietly. Dark matter played the first and most decisive role. Unlike ordinary matter, dark matter does not interact with radiation. In the early universe, normal matter was tightly coupled to photons. It could not collapse efficiently because radiation pressure pushed against gravitational contraction. Dark matter, unaffected by light, began clumping first. These early dark matter clumps became the seeds of future galaxies. As the universe expanded and cooled, normal matter finally decoupled from radiation. Gas began to fall into the gravitational wells created by dark matter halos. The deeper the well, the more efficiently gas could accumulate. If UGC 12,591 today resides within one of the most massive halos known for a spiral galaxy, that halo likely began forming early. Early formation matters because structure in the universe grows hierarchically. Small halos merge into larger ones. Regions that start slightly denser often end up much more massive. An early massive halo gains a head start. Gas falling into such a halo does not simply pile up randomly. It conserves angular momentum. Slight initial rotations are amplified as gas contracts. This conservation of angular momentum naturally leads to disk formation. Instead of collapsing into a spherical blob, gas spreads out into a rotating disk. The size and rotation speed of that disk depend on two main ingredients: the total mass of the halo and the angular momentum carried by the infalling gas. UGC 12,591 appears to have had both in abundance. There are two primary pathways for a galaxy to gain mass. One is through mergers with other galaxies. The other is through smooth accretion of gas from the surrounding cosmic web. Both processes likely contributed to UGC 12,591's growth, but the balance between them is crucial. Major mergers between galaxies of comparable size tend to disrupt spiral disks. Stars are thrown into random orbits. Gas clouds collide violently. The end product is often an elliptical galaxy, dominated by dispersion rather than rotation. UGC 12,591 does not show the hallmarks of such violent disruption in its recent history. Its disk remains coherent. Its rotation curve is smooth. That suggests it avoided major mergers after its disk was well established. This does not mean it never merged with anything. Minor mergers, where a large galaxy absorbs much smaller companions, are common. These events add mass without necessarily destroying the disk. Over billions of years, repeated minor mergers can significantly increase a galaxy's mass while preserving its spiral structure. In addition to mergers, smooth accretion plays an essential role. The universe is threaded with filaments of dark matter and gas, forming what is often called the cosmic web. Galaxies at the intersections of these filaments can continuously draw in fresh material. If UGC 12,591 sits at a favourable location within this web, it could have enjoyed a steady supply of gas over extended periods. That gas fuels star formation, building up the stellar disk gradually. The pace of this growth matters. Slow, steady accretion allows the disk to adjust and remain stable. Rapid, chaotic inflows are more likely to trigger instabilities. Simulations of galaxy formation suggest that the most massive spiral galaxies are those that formed their halos early and then grew primarily through smooth accretion rather than late-time major mergers. UGC 12,591 fits that description. Another factor contributing to its mass is the efficiency of star formation. Not all gas that falls into a galaxy turns into stars. Feedback from supernovae and active galactic nuclei can heat gas and prevent it from collapsing further. In very massive halos, however, gravity is strong enough to retain much of this gas despite feedback processes. In smaller galaxies, energetic events can blow gas out entirely, limiting growth. In a halo as massive as UGC 12,591's, outflows are less likely to escape permanently. Gas can cool again and continue forming stars. This retention ability contributes to long-term mass accumulation. There is also the question of timing. The early universe was denser and interactions were more frequent. If UGC 12,591 assembled a large fraction of its mass early, it would have had more time to settle into equilibrium and build a stable disk. Galaxies that form late or experience late major mergers often exhibit disturbed structures. UGC 12,591 appears mature, suggesting its formative period occurred long ago. Angular momentum distribution within the halo also influences final structure. If angular momentum is distributed smoothly, gas can settle into an extended disk. If it is uneven, the disk may be warped or unstable. The extended size of UGC 12,591's disk suggests a favourable angular momentum profile. Its stars orbit at extraordinary speeds, but their orbits remain organised. Building such a massive spiral is therefore not a matter of one dramatic event. It is the outcome of favourable initial conditions combined with long-term stability. Massive halos also influence cooling rates. In extremely massive halos, gas can become so hot that cooling becomes inefficient, potentially suppressing star formation. This may explain why UGC 12,591's current star formation rate is not especially high. It may have consumed much of its readily available cool gas earlier in its history. Over time, the galaxy transitions from active growth to maintenance. Another important aspect of massive galaxy formation is the interplay between the central supermassive black hole and the surrounding gas. Most large galaxies host black holes whose masses correlate with the properties of the bulge. Feedback from active galactic nuclei can regulate gas inflow, preventing runaway star formation. While specific measurements for UGC 12,591's black hole are limited, it likely follows similar scaling relations. Its central black hole may have contributed to regulating growth without halting it entirely. The balance between gas accretion, star formation, feedback, and dark matter halo growth is delicate. Small differences in initial density or environment can lead to large differences billions of years later. UGC 12,591 appears to represent a case where conditions aligned optimally for producing a giant spiral rather than an elliptical galaxy. It is worth emphasizing that such systems are rare. Most galaxies do not reach these extremes. The distribution of halo masses declines sharply at high values. The probability of forming and maintaining such a massive spiral is low compared to more typical outcomes. This rarity makes UGC 12,591 especially valuable for testing galaxy formation models. If simulations can reproduce its properties under realistic assumptions, confidence in those models increases. There is a temptation to think of building a monster as something chaotic or violent. In the case of UGC 12,591, the growth appears to have been steady and controlled. It is monstrous in scale, not in temperament. The galaxy did not need a catastrophic series of collisions to become massive. It needed time, a deep gravitational well, and favourable cosmic geography. What does an invisible structure of several trillion solar masses actually look like in theoretical models? How far does it extend? And how does it maintain stability across such immense distances? Hidden far beyond the last visible spiral arm, extending well past the faint glow of the outermost stars, lies the structure that truly defines UGC 12591. You cannot see it in optical images, you cannot trace its outline with a telescope in the traditional sense, and yet it outweighs everything luminous in the galaxy by a wide margin. This is the dark matter halo, the gravitational framework that makes the entire system possible. If the visible disk were all that existed, UGC 12591 would not look the way it does. Its stars would not orbit at more than 500 kilometers per second and remain bound. Its spiral structure would not persist across vast radii. The halo is not a decorative addition, it is the foundation. To understand how the halo holds everything together, it helps to think in terms of gravitational potential rather than simple attraction. A massive object creates a gravitational well. The deeper the well, the harder it is for objects to escape. In small galaxies, that well is relatively shallow. In clusters of galaxies, it is extraordinarily deep. UGC 12591 sits somewhere between those extremes, but closer to the cluster end than most spirals. Estimates place its total halo mass at several trillion times the mass of the Sun. The visible stars account for only a fraction of that. The halo likely extends far beyond the luminous disk, perhaps reaching a radius of over 1 million light-years. This scale matters. Gravity does not stop at the edge of visible light. It declines gradually with distance, and if mass continues to accumulate outward, the gravitational influence persists. In UGC 12591, the rotation curve suggests that mass continues increasing with radius long after visible matter tapers off. That is the signature of an extended halo. Dark matter halos are thought to form through hierarchical merging. Small clumps of dark matter combine to form larger structures. Over time, these structures grow, attracting both dark and ordinary matter. The halo that now surrounds UGC 12591 likely assembled through countless minor mergers and accretion events over billions of years. Unlike stars, dark matter does not radiate away energy. It does not cool and collapse into dense cores the way gas does. Instead, it remains relatively diffuse, forming a roughly spherical distribution around the galaxy. This diffuse nature is crucial. A concentrated mass at the centre would not sustain high rotation speeds at large radii. Only a broadly distributed halo can provide the necessary gravitational support across the entire disk. The halo's density profile determines how gravity behaves with distance. Simulations suggest that dark matter halos follow predictable patterns, with density highest at the centre and gradually declining outward. The precise shape of that decline influences the rotation curve. For UGC 12591, the rotation curve indicates a halo dense enough to maintain extreme velocities even far from the core. That means the halo's mass is not only large in total, but also structured in a way that spreads gravitational influence effectively. Another subtle aspect of halos is their interaction with the disk. The disk does not float independently inside the halo. The two components influence each other. The gravitational pull of the halo shapes the disk's thickness, stability, and susceptibility to instabilities like bars and spiral waves. In smaller galaxies, a weak halo may allow internal instabilities to grow unchecked. In extremely massive systems, the halo can dominate dynamics entirely. UGC 12591 appears to exist in a regime where the halo is strong but not disruptive. It anchors the disk without destroying its ordered rotation. One way to picture this is to imagine the visible galaxy as a thin, rotating sheet embedded inside a much larger invisible sphere. The sheet spins rapidly, but the sphere's gravity prevents it from dispersing. The halo also influences how gas behaves in the galaxy's outskirts. Gas clouds in the outer disk remain bound because of the halo's pull. Without it, they might drift away, reducing the galaxy's capacity for future star formation. There is also evidence from cosmological simulations that halos of this size can affect their surroundings on even larger scales. They can alter the motion of nearby dwarf galaxies and influence the distribution of intergalactic gas. In that sense, UGC 12591's halo is not merely a local feature, it shapes the environment around the galaxy as well. Despite its importance, the halo remains invisible to direct observation. Astronomers infer its presence from rotation curves, gravitational lensing, and large-scale structure patterns. Each method provides a different perspective, but all point to the same conclusion. The halo dominates the galaxy's mass budget. The idea that most of a galaxy's mass is invisible can feel counterintuitive. When we look at images of spiral galaxies, the luminous arms seem like the primary feature. In reality, they are tracers embedded within something much larger and more massive. For UGC 12591, this inversion of perception is especially pronounced. The halo must be extraordinarily massive to sustain its rotation. Another important factor is concentration. Halos of similar total mass can have different concentration parameters, meaning the relative distribution of mass toward the centre versus the outskirts varies. A more concentrated halo has stronger central gravity, while a less concentrated one spreads mass more evenly. Rotation curve modelling suggests that UGC 12591's halo is massive and moderately concentrated, allowing for high velocities without overly steep central acceleration. Over cosmic time, halos can evolve. Minor mergers add mass to the outskirts. Tidal interactions can redistribute material. But in the absence of major disruptions, the overall structure remains stable for billions of years. The stability of UGC 12591's halo is reflected in the smoothness of its rotation curve. Large irregularities would suggest recent disturbance. Instead, the curve appears steady and well-defined. There is also the matter of escape velocity. A halo this massive produces high escape speeds across the galaxy. That means even energetic events like supernova explosions are unlikely to eject gas permanently. The halo's gravitational grip is strong. This retention capacity likely contributed to the galaxy's long-term growth. Gas that might have escaped from a smaller system remained bound here, available for future star formation. It is important to remember that halos are not static shells. They are dynamic systems composed of countless dark matter particles moving in complex orbits. Their overall structure emerges from collective gravitational behaviour. While we cannot observe individual dark matter particles, we can observe their collective influence. In UGC 12591, that collective influence is unmistakable. The halo holds everything together not through rigidity, but through gravitational depth. It creates a potential well so deep that even stars moving at extreme speeds remain bound. This understanding shifts how we interpret the galaxy's identity. UGC 12591 is not merely a luminous disk with a surprising rotation speed. It is the visible component of a much larger invisible structure. If such massive halos exist around spiral galaxies, what does that tell us about the broader universe? Are there limits to how large these halos can become? And could there be systems even more extreme than this one, still waiting to be discovered in the quiet expanses beyond our current surveys? Long before UGC 12591 became a fully formed spiral galaxy, with 1 trillion stars moving in disciplined orbits, the universe itself was still settling into its basic patterns. The galaxy we see today carries within it a record of those early conditions, not written in words or images, but encoded in mass, motion, and structure. When astronomers study a system this extreme, they are not only learning about a single galaxy, they are also reading a chapter of the universe's early history that would otherwise be difficult to access. UGC 12591 did not acquire its size and speed recently. Galaxies do not suddenly become massive late in life without dramatic consequences. Its present-day properties strongly suggest that its foundations were laid early, when the universe was younger, denser, and more efficient at building large structures. In the early universe, matter was distributed in a way that looks almost smooth when viewed on very large scales. Tiny fluctuations existed, seeded during inflation, but those fluctuations were enough. Gravity amplifies differences. Regions that were slightly denser than average began pulling in more matter. Over time, those regions grew into the first dark matter halos. The most important detail here is timing. Halos that began forming early had more time to grow. They existed when the universe was denser, meaning there was more material nearby to draw in. An early start allowed certain halos to become much more massive than others. UGC 12591 appears to be associated with one of these early forming halos. This matters because dark matter halos set the stage for everything that follows. Once a halo forms, it becomes a gravitational anchor. Gas flows into it. That gas cools, stars form, disks take shape. The properties of the halo influence the size, rotation, and long-term stability of the galaxy that emerges. If UGC 12591's halo assembled a large fraction of its mass early, it would explain several of its defining traits. A deep gravitational well-established early would attract gas efficiently. It would allow star formation to proceed steadily over billions of years. It would also reduce the likelihood that later events could disrupt the disk. In contrast, halos that grow slowly or experience late major mergers often produce galaxies with disturbed morphologies or elliptical shapes. Timing is everything. Another clue pointing to early formation is the galaxy's extreme rotation speed. Angular momentum in galaxies is not created arbitrarily. It arises from tidal torques in the early universe when neighbouring regions of matter gravitationally interacted. The amount of angular momentum a halo acquires depends on its environment and formation history. If UGC 12591's halo experienced strong tidal torques early on, it could have acquired unusually high angular momentum. As gas fell into the halo, that angular momentum would be conserved, leading to the formation of a large, fast-spinning disk. This is not speculation pulled from thin air. Cosmological simulations consistently show that halo spin parameters are set early and evolve slowly. A halo that starts with high angular momentum tends to maintain that advantage. The galaxy's current rotation speed, then, is not an accident. It is a legacy of early cosmic conditions. There is also the matter of baryonic efficiency, how effectively a halo converts gas into stars. In the early universe, gas was more abundant. Cooling was efficient in massive halos. Star formation could proceed at high rates before feedback mechanisms became dominant. UGC 12591 likely experienced a prolonged period of efficient star formation early in its history. That would help explain its enormous stellar mass. Later, as gas reservoirs were depleted or heated, star formation would slow, leaving behind a mature, massive system. The fact that UGC 12591 is not currently undergoing an intense starburst supports this picture. Its most active growth phase is likely long past. Another revealing aspect is its apparent isolation. Galaxies in dense clusters experience frequent interactions and mergers, especially at later times. Those interactions can dramatically reshape galaxies. UGC 12591 does not appear to be in such an environment. This suggests it formed in a region of the universe that was rich in matter early on but did not become crowded later. Such regions exist along the filaments of the cosmic web, where material flows steadily inward without necessarily producing constant collisions. In the early universe, these filaments were even more effective conduits for matter. Gas could stream into halos along preferred directions, feeding growth without the violence of major mergers. This mode of growth leaves subtle signatures. Disks formed this way tend to be large and stable. Their rotation curves are smooth. Their stellar populations show evidence of extended formation histories rather than sudden bursts triggered by collisions. UGC 12591 matches that profile. Its size also tells us something about the scale of early density fluctuations. The existence of such a massive spiral implies that the primordial fluctuations that seeded its halo were among the larger ones within the distribution allowed by cosmological models. This does not contradict current understanding of the early universe. The distribution of fluctuations predicted by inflation allows for rare, high-density peaks. Those peaks are expected to produce the most massive structures we see today. UGC 12591 may represent one of those rare outcomes. There is a temptation to view the early universe as chaotic, but on large scales it followed remarkably consistent statistical rules. Rare does not mean unexpected, it means uncommon but allowed. Another window into the early universe comes from considering metallicity. As stars form and die, they enrich their surroundings with heavier elements. Older stellar populations tend to have lower metallicity because fewer generations of stars preceded them. While detailed metallicity measurements for UGC 12591 are challenging due to its distance, its overall maturity suggests a long history of star formation and chemical enrichment. That enrichment process would have begun early, reinforcing the idea of an early assembly. The halo itself also carries memory. Dark matter halos that form early tend to be more concentrated than those that form later. Concentration affects how steeply density rises toward the center. Rotation curve modeling hints that UGC 12591's halo is both massive and relatively well concentrated, consistent with early formation. This concentration helps explain why the galaxy can sustain high rotation speeds without instability. UGC 12591 also informs our understanding of how quickly structure emerged in the universe. Observations of distant galaxies already show that massive systems existed surprisingly early, within a few billion years of the Big Bang. UGC 12591 demonstrates that not only can massive galaxies form early, but they can also maintain ordered disk structures over cosmic time. That combination places strong constraints on galaxy formation models. Simulations must allow for early halo growth, efficient angular momentum acquisition, and long-term disk stability. If models fail to produce systems like UGC 12591, they are missing something essential about early cosmic conditions. Another implication concerns dark matter itself. The ability of dark matter halos to grow large early, without fragmenting or collapsing too quickly, depends on the properties of dark matter particles. Different dark matter models predict different small-scale behaviors. UGC 12591 does not single-handedly determine which model is correct, but its existence supports scenarios in which dark matter behaves as a cold, collisionless component that can form large, stable halos early. Warm or self-interacting dark matter models sometimes predict less concentrated halos or suppressed small-scale structure. Whether such models can accommodate galaxies like UGC 12591 is an active area of research. In this way, a single galaxy becomes relevant to particle physics and cosmology. Its rotation speed and mass distribution place constraints not just on galaxy formation, but on the fundamental nature of matter. There is also a broader lesson here about timescales. The extreme properties we observe today are not the result of recent events. They are the cumulative outcome of processes operating over billions of years. UGC 12591 reminds us that the universe rewards patience. Small initial differences given enough time can lead to extraordinary results. As we consider what this galaxy reveals about the early universe, it becomes clear that its story is not isolated. It connects to the formation of large-scale structure, the behavior of dark matter, the origin of angular momentum, and the efficiency of early star formation. Each of these threads points backward in time. At the very centre of almost every large galaxy, including systems far less massive than UGC 12591, sits an object that occupies an almost paradoxical role. It is tiny compared to the galaxy as a whole, yet it can influence the behaviour of gas and stars across enormous distances. This object is a supermassive black hole. For a galaxy as massive as UGC 12591, the presence of a supermassive black hole is not in doubt. Although direct measurements are challenging at a distance of roughly 400 million light-years, well-established correlations between galaxy bulge mass and black hole mass make its existence highly likely. The central bulge of UGC 12591 is substantial, and galaxies with comparable bulges typically host black holes with masses ranging from hundreds of millions to billions of solar masses. Still, even a billion solar mass black hole is small compared to a halo containing several trillion solar masses. This raises a natural question. If the dark matter halo dominates the galaxy's mass budget and determines its large-scale rotation, what role does the central black hole actually play? The answer lies not in total mass, but in regulation. Supermassive black holes exert intense gravitational influence in their immediate surroundings. Within a small central region, their gravity dominates over that of stars and gas. But their most significant impact on galactic evolution comes not from gravity alone, but from energy feedback. When matter falls toward a black hole, it does not disappear quietly. As gas spirals inward, it forms an accretion disk. Friction and compression heat this gas to extraordinary temperatures, causing it to emit radiation across the electromagnetic spectrum. In some cases, powerful jets of particles are launched outward at nearly the speed of light. This process, known as active galactic nucleus activity, can inject enormous amounts of energy into the surrounding galaxy. For UGC 12591, there is no clear indication that it is currently hosting a luminous active nucleus. It does not appear to be a quasar or a bright radio galaxy. However, that does not mean it never was. Many galaxies go through active phases early in their histories, when gas supplies are abundant. During such phases, the black hole can influence star formation across the galaxy. If too much gas cools and collapses into the central regions, star formation can proceed at runaway rates. The resulting stellar feedback combined with black hole activity can heat or expel gas, limiting further collapse. In massive halos, this feedback does not necessarily eject gas entirely. Instead, it can regulate the rate at which gas cools and forms stars. In this way, the black hole acts as a thermostat. For a galaxy as massive as UGC 12591, this regulatory mechanism may have been essential. Without some form of feedback, its early gas accretion could have led to an even more rapid buildup of stars, potentially destabilizing the disk or exhausting gas supplies too quickly. The balance between cooling and heating is delicate. In smaller galaxies, feedback can dominate, blowing gas out entirely. In extremely massive halos, cooling can become inefficient because gas reaches high temperatures. UGC 12591 likely sits in an intermediate regime where both processes matter. Another well-known relationship in astrophysics connects the mass of a supermassive black hole to the velocity dispersion of stars in the galactic bulge. This correlation suggests a deep link between central black hole growth and the overall gravitational potential of the galaxy. For UGC 12591, the extreme rotation speed of the disk reflects a deep gravitational well created primarily by dark matter. The bulge, which likely hosts the black hole, also contributes to the central gravitational field. The black hole's mass is expected to scale with the bulge's mass and stellar velocity dispersion. While the black hole's gravitational influence does not extend far enough to affect outer disk rotation directly, its growth history may parallel that of the halo. Both likely assembled significant mass early in cosmic history. This parallel growth is consistent with hierarchical formation models. As the halo grew through mergers and accretion, gas flowed inward, feeding both star formation and black hole accretion. The galaxy and its central black hole evolve together. In many massive galaxies, evidence suggests that black hole feedback plays a role in shutting down star formation at later times. The energy released during active phases can heat surrounding gas, preventing it from cooling efficiently. This leads to a decline in star formation, leaving behind an older stellar population. UGC 12591's current moderate star formation rate fits this scenario. Its most intense growth phase may be in the past. The black hole could have contributed to regulating that transition. There is also a structural aspect to consider. The presence of a massive bulge often correlates with disk stability. A central concentration of mass can help suppress certain types of instabilities within the disk. In UGC 12591, the bulge is substantial, though not so dominant as to erase the disk entirely. The balance between bulge, disk, and halo mass appears finely tuned. The halo provides large-scale gravitational anchoring. The bulge contributes central stability. The disk maintains organized rotation. This interplay forms a multi-component system in equilibrium. It is important not to overstate the black hole's role. In terms of total mass, it is a minor component compared to the halo. It does not determine the galaxy's extreme outer rotation speed. That distinction belongs firmly to dark matter. However, black holes influence the internal evolution of galaxies in ways that can shape long-term structure. They help regulate gas flows, control star formation rates, and maintain thermal balance within central regions. The idea of galactic balance therefore involves more than just rotation versus gravity. It includes the flow of gas inward and outward, the heating and cooling cycles within the halo, and the energy feedback from both stars and black holes. In a system as massive as UGC 12591, these processes must have operated for billions of years without catastrophic disruption. Another interesting consideration is that supermassive black holes can also merge. If UGC 12591 experienced minor mergers with smaller galaxies, each bringing its own central black hole, those black holes may have eventually merged into a larger one at the centre. Such mergers release gravitational waves and can slightly alter central dynamics. While direct evidence for such events in UGC 12591 is unavailable due to distance, hierarchical growth models predict that some level of black hole merging is inevitable over cosmic time. All of these factors reinforce a broader theme. Galaxies are not simple rotating disks of stars. They are complex systems composed of multiple interacting components: dark matter halos, stellar disks, gas reservoirs, bulges, and central black holes. UGC 12591's extreme rotation and mass make it an especially clear example of this complexity. The halo holds the outer regions together. The bulge and black hole regulate the inner regions. Gas flows connect the two. Over billions of years, these components settle into a long-lived equilibrium. That equilibrium is not static. It evolves slowly. Star formation declines. Gas reservoirs shrink or are replenished. Minor mergers add mass. The black hole grows gradually, yet the overall structure remains coherent. Considering the scale of UGC 12591, it is natural to wonder whether even larger or faster spiral galaxies could exist. If a halo slightly more massive or an angular momentum distribution slightly more favourable emerged early in the universe, could a system exceed even this record? It is tempting to assume that records in astronomy represent hard limits. The largest star, the most massive black hole, the fastest rotating galaxy. But history has a way of undoing that assumption. Again and again, what once seemed extreme becomes merely a point along a broader spectrum as observations improve and surveys deepen. So when UGC 12591 is described as the fastest known spiral galaxy, the more interesting question is not whether the record will stand forever, but whether the universe itself permits systems even larger and more extreme. To explore that question, we have to step back from any single galaxy and think statistically. Galaxies do not form in isolation from probability. They emerge from initial conditions set in the early universe, shaped by the distribution of matter, the strength of gravity, and the expansion of space. Those conditions produce a wide range of outcomes. Some are common, some are rare, a few sit at the far edges of what is possible. UGC 12591 clearly occupies one of those edges. The first point to consider is whether there is a theoretical upper limit to the size or mass of a spiral galaxy. From a purely gravitational standpoint, there is no absolute cutoff written into the laws of physics. Gravity does not stop working beyond a certain mass. Dark matter halos can, in principle, continue growing as long as material is available to accrete. What does impose practical limits are processes that disrupt disk structure. As halos grow more massive, their merger histories tend to become more violent. Large halos are more likely to encounter other large halos. When two massive systems collide, the energy involved is enormous. Disks are fragile under those conditions. Stars are scattered into random orbits. Gas clouds are shocked and heated. The orderly rotation that defines a spiral galaxy can be lost. This is why the most massive galaxies in the universe are typically elliptical rather than spiral. Elliptical galaxies can be far more massive than UGC 12591. Some contain several trillion stars. Their dark matter halos can exceed 10 trillion solar masses, but their internal motions are dominated by random velocities rather than organized rotation. UGC 12591 sits at a delicate boundary. It is massive enough to rival smaller ellipticals in total mass, yet it has retained a rotating disk. That alone suggests it formed under unusually favourable conditions. For a spiral galaxy to grow even larger than UGC 12591, several constraints would need to be satisfied simultaneously. Its dark matter halo would need to form early, gaining a head start in mass accumulation. Its environment would need to remain relatively calm after disk formation, avoiding major mergers. Its angular momentum would need to be high enough to support a large disk without collapse. Feedback processes would need to regulate star formation, without shutting it down entirely. Each of these requirements is individually plausible. Combined, they become increasingly rare. Rarity, however, does not mean impossibility. Cosmological simulations show that the distribution of halo masses extends to very high values, though with steeply declining probability. For every 1,000 modest halos, there may be one exceptionally massive one. For every million, perhaps one that is truly extreme. UGC 12591 may represent one of those statistical outliers. The universe is vast enough that even extremely rare outcomes can occur somewhere. Another factor to consider is observational bias. Our knowledge of galaxy populations is limited by what we can detect and measure reliably. Large, fast-rotating spiral galaxies are easiest to identify when they're relatively nearby and well-oriented for observation. Inclination matters, distance matters, signal-to-noise matters. It is entirely possible that galaxies comparable to, or even larger than UGC 12591 exist, but have not yet been recognized as such. They may be more distant. They may be oriented face-on, making rotation measurements difficult. They may lie in regions of the sky that have not been surveyed in sufficient detail. As surveys improve, especially in radio wavelengths where neutral hydrogen can be traced far into galactic outskirts, the census of massive spirals may expand. Future instruments will play a critical role here. More sensitive radio arrays can measure rotation curves at greater distances. Larger optical telescopes can refine mass estimates. Gravitational lensing surveys can detect massive halos even when their galaxies are faint. With each improvement, the boundary of what is known shifts outward. Another important point is that size and mass are not the same thing. A galaxy can be physically large without being exceptionally massive if its density is low. Conversely, it can be compact yet extremely massive. UGC 12591 is notable because it combines large physical extent with high mass and extreme rotation. Any galaxy surpassing it would likely need to exceed it in halo mass rather than just disk size. There is also the question of how rotation speed scales with mass. Increasing halo mass does not automatically guarantee higher disk rotation speed. The relationship depends on how angular momentum is distributed between the halo and the disk. Some halos may be massive but have relatively low spin parameters, resulting in slower rotating disks. Others may have higher spin, producing faster rotation for a given mass. UGC 12591 appears to have both high mass and favourable angular momentum. Finding another galaxy that exceeds it would require a similarly fortunate combination, perhaps even more extreme. Then there is cosmic time. The universe is still evolving. Dark matter halos continue to merge. Galaxies continue to grow. It is possible that even larger spiral galaxies will form in the future, though the declining density of the universe makes efficient growth more difficult over time. Most massive halos form early. Late-time growth is slower and more merger-driven, favouring elliptical outcomes. That suggests that the window for forming extremely massive spirals may already be closing. UGC 12591 may therefore represent a peak outcome of a process that was more viable earlier in cosmic history. That does not rule out the existence of others like it, but it suggests they would also be relics of early formation rather than products of recent growth. Another subtle constraint comes from cooling physics. In very massive halos, gas can become so hot that it struggles to cool efficiently. Without cooling, gas cannot collapse to form stars or settle into a disk. This effect is thought to limit the maximum mass of star-forming disks. UGC 12591 may sit near that cooling threshold. Its halo is massive enough to retain gas, but not so massive that cooling is completely suppressed. A significantly larger halo might struggle to form or maintain a disk at all. This introduces a physical, though not absolute, upper limit to spiral galaxy mass. From this perspective, UGC 12591 may be close to the maximum mass at which a spiral disk can remain stable and luminous. Larger halos may exist, but their galaxies may be predominantly elliptical. There is also evidence from simulations that disks become increasingly unstable as halo mass increases. Bars become more prominent. Vertical heating thickens the disk. Eventually, the distinction between disk and spheroid blurs. UGC 12591 appears to have avoided these outcomes, but pushing further might not be sustainable. Even so, the universe has a habit of surprising us. What seems implausible often turns out to exist somewhere, quietly, waiting for the right instrument to notice it. It is also worth remembering that the phrase largest depends on definition. Largest by mass, largest by radius, largest by number of stars, fastest by rotation speed. Each metric may produce a different record holder. UGC 12591 holds a specific distinction: extreme rotation speed for a spiral galaxy. Another system might surpass it in mass but rotate more slowly. Another might be physically larger but less dense. So when asking whether even larger galaxies exist, the answer may depend on what aspect of larger we care about. The more important takeaway is not whether UGC 12591 will always hold a record, but what its existence tells us. It demonstrates that spiral galaxies can grow larger and faster than once assumed. It expands the known parameter space. It forces models to accommodate more extreme outcomes. That expansion of understanding is the real value. As surveys continue and simulations improve, UGC 12591 may gain companions at the extreme end of the spiral galaxy population, or it may remain a singular case, a rare alignment of early conditions and long-term stability. Either outcome is informative. If similar systems are found, they will help define a new class of massive spirals. If not, UGC 12591 will stand as a unique benchmark, illustrating how far galaxy formation can be pushed without breaking. When galaxies approach these extremes, do our current models of gravity and matter remain sufficient? Or do such systems expose subtle tensions that hint at deeper gaps in our understanding? At some point in every scientific investigation, the focus shifts from explaining what we see to questioning how confident we are in the tools we use to explain it. UGC 12591 brings us precisely to that moment. Its mass, its rotation speed, and its apparent stability all fit within the broad framework of a modern cosmology, yet they do so while pressing firmly against the edges of that framework. Nothing breaks outright. No equation collapses, but the margins begin to feel thin. This is where gravity meets mystery. Our current models of galaxies rest on a layered foundation. At the base lies gravity, described by Newton on everyday scales and by Einstein on cosmic ones. Built on top of that are models of dark matter, usually assumed to be cold, collisionless, and dominant on galactic scales. Layered above that are simulations of gas dynamics, star formation, feedback from stars and black holes, and the statistical distribution of matter seeded in the early universe. UGC 12591 does not reject this structure. Instead, it demands that every layer operate at near maximum capacity simultaneously. To begin with, consider the dark matter halo. The halo mass inferred for UGC 12591 is extreme for a spiral galaxy. Several trillion solar masses is not unheard of in galaxy clusters or giant ellipticals, but for a disk galaxy that has retained ordered rotation, it is exceptional. Models predict such halos should exist, but rarely. They sit on the far tail of the mass distribution. That alone does not invalidate the models. Rare outcomes are expected in a universe as large as ours. But rarity forces scrutiny. When something appears at the edge of predicted behavior, it becomes a stress test. The first stress point lies in halo formation. Cosmological simulations predict how many halos of a given mass should exist at different epochs. These predictions depend sensitively on assumptions about dark matter properties and the initial conditions of the universe. UGC 12591 appears consistent with those predictions, but only just. Its inferred halo mass places it near the upper boundary for halos expected to host spiral galaxies rather than ellipticals. If more galaxies like this were found, models would need to explain not just one rare case, but a population. If none are found, the question becomes why this one survived as a spiral. Either outcome feeds back into how we understand halo growth. Another pressure point appears in angular momentum retention. One long-standing problem in galaxy formation theory is the so-called angular momentum problem. Early simulations tended to produce disks that were too small and too slow because gas lost angular momentum during collapse. Modern simulations have largely resolved this issue through improved feedback modelling, but UGC 12591 pushes the solution to its limit. Its disk is not just large, it is rotating extraordinarily fast. This implies that its baryonic matter retained a very high fraction of its initial angular momentum. That retention must have persisted through billions of years of evolution, including minor mergers and gas inflows. Our models allow this in principle, but they do not guarantee it. The conditions must align carefully. Feedback must be strong enough to prevent catastrophic collapse, but not so strong that it ejects gas. Mergers must be small enough to avoid disruption. Gas inflow must be steady rather than chaotic. UGC 12591 suggests that such a finely balanced evolutionary path is possible, but it also highlights how narrow that path may be. Then there is the question of disk stability. Rapidly rotating disks are susceptible to instabilities. Bars can form, spiral arms can thicken, vertical heating can turn thin disks into puffed-up structures. Over time, these effects can erode the distinction between disk and spheroid. Yet UGC 12591 remains recognisably spiral. This implies that stabilising influences have been effective over long timescales. A massive halo can help, as can a substantial bulge. But again, the balance must be precise. Too much central concentration and the disk could be overwhelmed. Too little and instabilities grow. Current models can reproduce stable disks, but doing so at this mass scale is challenging. UGC 12591 does not contradict simulations, but it occupies a corner of parameter space where small changes matter. Gravity itself also enters the conversation. The rotation curves of galaxies were one of the original motivations for proposing dark matter. Most of the time, dark matter explains observations elegantly, but extreme systems always invite alternative questions. Could gravity behave differently at very low accelerations or very large scales? Modified gravity theories propose adjustments to Newtonian dynamics that reproduce flat rotation curves without dark matter. These theories often work well for typical galaxies, but they struggle with systems like UGC 12591. The magnitude of the rotation speed here is not modest. It is extreme. Any modification to gravity that explains UGC 12591 without dark matter would need to produce a gravitational effect equivalent to several trillion solar masses of unseen matter. That is a tall order. Moreover, such modifications must also remain consistent with gravitational lensing, galaxy cluster dynamics, and the cosmic microwave background. UGC 12591 does not break modified gravity models outright, but it makes their task significantly harder. In that sense, the galaxy strengthens the case for dark matter as a real, dominant component rather than a convenient placeholder. Still, the fact that we rely on an unseen component to explain such systems is itself a reminder of the limits of our knowledge. We model dark matter halos using mathematical profiles derived from simulations, not from direct observation. We assume properties for dark matter particles that have not yet been confirmed in laboratories. UGC 12591 works within those assumptions, but it does not verify them at a fundamental level. There is also the issue of baryonic physics. Star formation and feedback processes are notoriously complex. They involve turbulence, magnetic fields, radiation pressure, and chemical processes that operate across a wide range of scales. In simulations, these processes are often approximated. Subgrid models represent collective behavior rather than individual events. For typical galaxies, these approximations work reasonably well. For extreme systems, small inaccuracies can accumulate. UGC 12591 tests those approximations. If feedback was slightly stronger, would its disk survive? If cooling was slightly less efficient, would its stellar mass be lower? If early mergers were more frequent, would it have become elliptical? The fact that it exists suggests that our models are at least capable of producing such outcomes. The fact that such outcomes are rare suggests that the window is narrow. Another area where uncertainty creeps in is measurement itself. Rotation curves rely on accurate distance estimates, inclination corrections, and assumptions about circular motion. While UGC 12591's measurements are robust, all observations carry uncertainty. Astronomers are cautious about declaring absolute limits based on a small number of extreme cases. One galaxy does not redefine the universe. It does, however, signal where attention should be focused. There is also the broader context of large-scale structure. Dark matter halos are not isolated objects. They form within a cosmic web. Their growth depends on environment. Filaments supply matter. Voids starve it. UGC 12591's environment appears conducive to steady growth without frequent disruption. Models must account not just for individual halos, but for the network they inhabit. When gravity meets mystery in this way, Science does not stop. It refines. Models are adjusted, simulations are rerun, observations are targeted. UGC 12591 has already influenced how astronomers think about the upper limits of spiral galaxies. It has encouraged searches for similarly extreme systems. It has prompted closer examination of halo mass distributions and disk stability criteria. Importantly, it has not forced a crisis. That distinction matters. A crisis occurs when observations flatly contradict theory. UGC 12591 does not do that. Instead, it exposes the edges of confidence. It reminds us that our models are not complete descriptions of reality, but tools that work within certain domains. At the edges of those domains, uncertainty grows. There is a quiet humility in acknowledging that. The universe is not obligated to conform to our expectations. It operates according to its own rules, which we approximate as best we can. UGC 12591 sits calmly within those rules, even as it challenges our intuition about scale and speed. The question becomes less about whether our models can accommodate this galaxy, and more about what it teaches us about the universe as a whole. Does it represent a rare statistical fluke, or does it hint at a population we have not yet fully recognized? Occasionally, an object appears that is so extreme it invites a question deeper than mass, speed, or structure. It invites a question about the rules themselves. UGC 12591 does exactly that. Once dark matter is invoked, and the numbers still feel astonishing, the mind naturally drifts toward a more fundamental possibility. What if our understanding of gravity, the force holding everything together, is incomplete? This question does not arise because gravity fails in ordinary situations. Newton's laws describe planetary motion with exquisite accuracy. Einstein's general relativity predicts gravitational lensing, time dilation, and black holes with remarkable precision. On human and solar system scales, gravity behaves exactly as expected. The mystery appears when gravity is applied across tens or hundreds of thousands of light years. Galaxies were the first place where this tension became obvious. When astronomers measured the rotation of spiral galaxies in the mid-20th century, the mismatch between visible mass and observed motion was unexpected. Stars far from galactic centers were moving too fast. Something was missing. The dominant response was to assume missing matter rather than faulty laws, because gravity works so well everywhere else. Dark matter became the simplest explanation. But simplicity does not mean certainty. Over the years, some researchers proposed an alternative path. Instead of adding unseen matter, they suggested altering how gravity behaves at extremely low accelerations. These ideas are often grouped under the umbrella of modified gravity theories. One of the most discussed is modified Newtonian dynamics, commonly abbreviated as MOND. In this framework, Newton's laws are adjusted when accelerations fall below a certain threshold. At those low accelerations, gravity becomes effectively stronger than classical physics predicts. MOND can reproduce flat rotation curves in many galaxies using only visible matter. For typical spiral galaxies, it often works surprisingly well. This success has kept such theories alive, even as dark matter remains the dominant paradigm. However, UGC 12591 presents a serious challenge to these alternatives. The rotation speeds involved here are not modest deviations, they are extreme. To explain a rotation curve flattening at over 500 km per second using modified gravity alone would require an enormous enhancement of gravitational strength across a vast radius. In practical terms, MOND-like theories would need to generate the gravitational equivalent of several trillion solar masses without invoking dark matter. That is difficult to achieve without breaking consistency elsewhere. There is also the issue of scaling. Modified gravity theories are often calibrated to match typical galaxies. When pushed to extremes, they can struggle. Parameters that fit average spirals may not fit outliers like UGC 12591 without adjustment. Adjusting parameters on a case-by-case basis weakens predictive power. Another constraint comes from gravitational lensing. Dark matter not only explains rotation curves, it explains how galaxies bend light from background objects. Lensing measurements often align well with dark matter halo models. Modified gravity theories must also reproduce these lensing effects. Some extensions attempt to do so, but the agreement is not always as robust, especially in complex systems. UGC 12591's inferred halo mass implies strong lensing effects, even if subtle due to distance. Any gravity-only explanation must account for this as well. Then there is the cosmic microwave background, the afterglow of the Big Bang. The pattern of temperature fluctuations in this background radiation is sensitive to the amount and behavior of matter in the early universe. Dark matter plays a central role in matching those observations. Modified gravity theories face significant challenges in reproducing these large-scale features without introducing additional components that behave very much like dark matter anyway. This creates a curious situation. Many alternative gravity theories end up reintroducing unseen fields or particles to remain viable, blurring the distinction between modified gravity and modified dark matter. UGC 12591 reinforces this tension. Its existence does not rule out alternative gravity outright, but it narrows the space in which such theories can operate comfortably. There is also the question of consistency across scales. Gravity must explain not just one galaxy, but galaxy clusters, cosmic filaments, and the expansion history of the universe. A theory that works only for isolated galaxies but fails elsewhere is incomplete. Dark matter models, while still lacking direct particle detection, provide a unified explanation across these scales. Modified gravity models often excel in one domain while struggling in others. That does not mean the matter is settled. Science remains open to revision. But extreme systems like UGC 12591 act as stress tests. They force alternative ideas to confront the full range of observed behavior. Another subtle issue is the shape of rotation curves. Modified gravity often predicts specific curve shapes tied closely to visible mass distribution. In UGC 12591, the rotation curve remains high and smooth, even where visible matter declines sharply. Explaining that smoothness without an extended mass component is challenging. The question, do we truly understand gravity, therefore has a layered answer. On many scales, yes. On the largest and faintest scales, perhaps not fully. UGC 12591 does not tell us that gravity is wrong. It tells us that gravity, as we observe it, operates within a universe dominated by components we do not yet directly understand. It is also possible that the answer involves both dark matter and subtle modifications to gravity. Hybrid models exist, exploring whether dark matter interacts weakly with itself or with ordinary matter in ways that alter halo structure. These models remain speculative but demonstrate that the theoretical landscape is still active. What is striking is that even with uncertainty at the deepest level, the universe remains coherent. Galaxies form, disks rotate, structures persist. Whatever the ultimate explanation, it produces a universe that works. UGC 12591 reminds us that our current theories are effective approximations, not final truths. They describe behavior accurately enough to predict and explain, but not completely enough to satisfy curiosity at every level. That is not a failure. It is a natural stage in scientific progress. The role of extreme objects is to highlight where questions remain open. Ordinary systems confirm what we already know. Extraordinary ones show us where to look next. If gravity and dark matter can accommodate UGC 12591, what does that mean for our own place in the universe, How typical or atypical is the environment we inhabit compared to such giants? Most of what holds the universe together does not shine. That statement sounds dramatic at first, but it is simply a reflection of measurement. When astronomers inventory the cosmos, counting stars, gas and dust, they discover that all luminous matter combined accounts for only a small fraction of the total mass-energy budget. The rest is dominated by components we cannot see directly. Dark energy drives cosmic expansion. Dark matter sculpts structure. Ordinary matter, the kind that forms planets and people, is the minority. UGC 12,591 makes this imbalance impossible to ignore. When we describe it as one of the fastest rotating spiral galaxies known, we are really describing the behavior of a system whose visible disk is embedded inside an invisible gravitational structure several times more massive than the stars themselves. The spiral arms are the trace. The halo is the substance. Living in a dark matter universe means accepting that this pattern is not exceptional. It is the rule. Every galaxy we observe is believed to reside within a dark matter halo. The Milky Way, Andromeda, distant ellipticals, small dwarf galaxies, even faint irregular systems all appear to require unseen mass to explain their dynamics. UGC 12,591 simply magnifies the effect to an extreme. Consider our own galaxy. The Sun orbits the centre of the Milky Way at about 220 kilometers per second. If only visible matter were present, that speed would not be sustainable at our distance from the centre, far beyond the visible disk. UGC 12591 far beyond the visible disk. UGC 12,591 follows the same principle, but at a far greater scale. Its halo must be several trillion times the mass of the Sun. Its disk rotates at over 500 kilometers per second. Its gravitational well is deep and extensive. This leads to an important realization. We do not merely study dark matter as an abstract cosmological concept. We exist within it. The solar system moves through the Milky Way's halo constantly. Every star in every galaxy is influenced by it. It defines the scaffolding of cosmic structure. Dark matter shapes the universe from the larger scales to the scales of galaxies. Without dark matter, the early universe would have evolved very differently. Ordinary matter, coupled to radiation in the first hundreds of thousands of years after the Big Bang, could not collapse efficiently on its own. Dark matter unaffected by radiation pressure began clumping earlier. Those clumps became gravitational anchors. Gas fell in later, forming stars and galaxies. In this sense, dark matter preceded visible structure. UGC 12,591, with its massive halo, likely traces one of the larger early clumps in the primordial density field. Its existence reflects how initial conditions evolved over billions of years. Living in a dark matter universe also means that visible structure is only part of the story. When we observe a galaxy cluster, the galaxies themselves are embedded in a much larger halo that dominates the cluster's mass. Gravitational lensing measurements reveal this clearly. The bending of light around clusters corresponds to far more mass than can be accounted for by luminous matter. Even individual galaxies can act as gravitational lenses, their halos subtly distorting background light. UGC 12,591's halo likely contributes to such lensing effects, though at its distance and orientation the effect may be subtle. Nevertheless, its gravitational influence extends far beyond its bright disk. There is a conceptual shift required here. In everyday experience, mass and light are often correlated. A brighter object feels heavier. In the universe, that intuition fails. The brightest galaxies are not necessarily the most massive. The most massive structures are not necessarily the most luminous. Dark matter breaks that correlation. For UGC 12,591, the visible spiral is impressive, but the invisible halo defines its true mass. This realization carries philosophical weight, but it is grounded in data. Rotation curves, lensing, cosmic microwave background measurements, and large-scale structure surveys all converge on the same conclusion. Dark matter is a dominant component. Still, its fundamental nature remains unknown. Laboratory experiments continue searching for dark matter particles. Underground detectors attempt to capture rare interactions. Particle accelerators probe energy scales where dark matter candidates might appear. Astronomical observations search for indirect signatures, such as gamma rays from annihilation events. So far, none have provided definitive detection. This absence of direct detection does not negate the gravitational evidence. It does, however, remind us that we are living with an incomplete picture. UGC 12591 does not reveal what dark matter is made of. It reveals what dark matter does. It builds deep gravitational wells. It sustains extreme rotation. It allows spiral galaxies to grow massive without disintegrating. Another implication of living in a dark matter universe concerns structure formation. The cosmic web, the vast network of filaments and nodes connecting galaxies, is shaped primarily by dark matter. Galaxies form where dark matter density peaks. UGC 12591 likely sits within one of these nodes, or along a filament that fed it material over billions of years. The distribution of galaxies across the sky mirrors the distribution of dark matter. We see luminous traces outlining an invisible skeleton. This skeleton determines not just where galaxies form, but how they interact. The gravitational pull between galaxies is mediated by their halos. When two galaxies approach, it is not merely their stars interacting. It is the overlap of extended dark matter structures. In the case of UGC 12591, its massive halo would exert influence on neighbouring systems, even if they remain at considerable distances. There is also a more subtle everyday implication. Because we move through the Milky Way's halo, dark matter passes through Earth continuously. Estimates suggest that dark matter particles stream through our planet in enormous numbers every second. They do so without interacting noticeably, but their presence is constant. Living in a dark matter universe is not metaphorical, it is literal. The difficulty lies in perception. Our senses are tuned to electromagnetic radiation. We see light, we feel heat, we detect matter through touch. Dark matter interacts primarily through gravity, which is weak compared to electromagnetic forces on small scales. That makes it elusive in everyday contexts. Yet on galactic scales, gravity dominates. UGC 12591 demonstrates that gravity's dominance becomes even more striking when dark matter halos reach extreme masses. The visible disk becomes a minority component within a vast invisible structure. This shifts how we think about galactic identity. A galaxy is not just its stars, it is the total mass distribution, luminous and dark. Another important consequence is that galaxy evolution cannot be understood without considering halos. Star formation rates, gas inflows, feedback efficiency, disk stability, merger outcomes all depend on halo properties. UGC 12591's halo likely influenced every stage of its history, from early gas accretion to present-day rotation. In simulations of the universe, dark matter is often represented first. N-body simulations track billions of dark matter particles interacting gravitationally. These simulations produce the cosmic web. Only after this framework forms do researchers add gas and model star formation. The visible universe emerges from an invisible template. Living in a dark matter universe also means that the ultimate fate of galaxies is tied to halo dynamics. As the universe expands and dark energy accelerates that expansion, halos will become increasingly isolated. Galaxies outside a local group will drift beyond observational reach over immense timescales. UGC 12591, far beyond the Milky Way, is already part of that distant cosmic landscape. Its light has travelled hundreds of millions of years to reach us. Its halo, enormous as it is, remains confined to its local gravitational domain. From a broader perspective, the dark matter framework provides coherence. It explains why galaxies rotate as they do. It explains how clusters remain bound. It explains large-scale structure patterns. UGC 12591 reinforces this coherence by demonstrating how the framework holds even under extreme conditions. The galaxy does not defy gravity. It illustrates gravity operating within a universe dominated by unseen mass. There is something grounding about that realization. The universe is not chaotic. It is structured, but much of that structure is hidden from direct view. If this galaxy lives within such an immense halo, how does it compare directly to our own Milky Way? What differences in mass, rotation, and environment separate us from such a giant? Set beside a galaxy like UGC 12591, the Milky Way suddenly feels more specific, more conditional, and less inevitable than it often does in our imagination. We tend to think of our home galaxy as a standard example, a typical spiral quietly rotating in the cosmic night. But extreme systems have a way of reframing what typical actually means. By looking carefully at how UGC 12591 differs from the Milky Way, we gain a clearer understanding of why our galaxy looks the way it does, how it came to be, and what limits shape its future. Start with rotation. The Sun orbits the centre of the Milky Way at roughly 220 kilometers per second. That speed is already difficult to grasp on human scales, yet it is less than half the rotation speed measured in the outer disk of UGC 12591. This difference is not cosmetic. It reflects a fundamental contrast in gravitational depth. The Milky Way's dark matter halo is estimated to contain on the order of 1 to 2 trillion solar masses. That places it among large spiral galaxies, but well below the extreme end of the distribution. UGC 12591's halo appears to be several times more massive. The deeper the gravitational well, the faster stars can orbit without escaping. Rotation speed is not an isolated property. It is a direct expression of halo mass. This means that if the Milky Way was spinning at 500 kilometers per second at the Sun's radius, it would not look like the galaxy we know. Its halo would need to be far more massive. Its entire formation history would have been different. The comparison highlights something important. Galaxies are not interchangeable outcomes of cosmic evolution. Small differences in early conditions lead to very different present-day structures. The Milky Way did not miss out on becoming a giant like UGC 12591. It followed a different path. One of the most consequential differences lies in mass assembly history. Evidence suggests that the Milky Way experienced a relatively quiet merger history compared to many other large galaxies. It has absorbed smaller satellite galaxies over time, but it has avoided recent major mergers with galaxies of comparable size. That calm history helped preserve its thin disk and moderate rotation speed. It also limited how much mass it could accumulate. Major mergers bring mass quickly, but they also disrupt disks. Avoiding them preserves structure but constrains growth. UGC 12591 appears to have achieved both large mass and disk preservation, but doing so likely required a specific combination of early halo formation, favourable angular momentum, and environmental isolation. The Milky Way's circumstances did not align in quite the same way. Another contrast involves angular momentum. The Milky Way's spin reflects the angular momentum it acquired during early tidal interactions in the young universe. That angular momentum was sufficient to produce a large spiral disk, but not an extreme one. UGC 12591's angular momentum appears to be unusually high. That difference likely originates in early cosmic geometry, the relative positions and motions of neighbouring matter, overdensities during halo formation. These are not controllable variables, they are statistical outcomes. This underscores a key point. The Milky Way is not a baseline. It is one realization among many possible outcomes. The size of the stellar disk also illustrates this. The Milky Way's visible disk spans roughly 100,000 light-years in diameter. UGC 12,591's disk is significantly larger, extending perhaps several 100,000 light-years. Disk size correlates with halo size and angular momentum distribution. A larger halo can host a larger disk, provided angular momentum is sufficient to prevent collapse. Our galaxy sits comfortably within a regime that allows long-term disk stability without pushing physical limits. UGC 12,591 sites much closer to those limits. That proximity to limits matters when thinking about stability. The Milky Way's disk is relatively thin and dynamically cool. Stars orbit in well-defined planes with modest random motion. This is consistent with a galaxy that has not experienced strong recent disturbances. In more massive systems, disks tend to thicken. Random motions increase. Stability becomes harder to maintain. UGC 12,591's disk appears thicker and more massive, suggesting it has navigated this challenge successfully, but likely at the cost of a more dynamically heated structure. Another instructive difference involves star formation. The Milky Way forms stars at a moderate rate, roughly 1 to 2 solar masses per year. It retains enough cold gas to continue star formation for billions of years at that pace. UGC 12,591, despite its mass, does not appear to be forming stars at an especially high rate today. This suggests that much of its star formation occurred earlier. Its halo may now be so massive that gas remains hot and less able to cool efficiently. This comparison hints at a broader trend. More massive halos tend to quench star formation earlier. The Milky Way's intermediate mass allows it to sustain star formation longer. In this sense, our galaxy occupies a middle ground between small, gas-rich spirals and massive quenched systems. The presence of supermassive black holes also fits into this picture. The Milky Way's central black hole has a mass of about 4 million solar masses. That is large by everyday standards, but small compared to black holes in more massive galaxies. UGC 12,591 likely hosts a much larger black hole, potentially hundreds of millions of solar masses. That difference reflects the scaling relationship between bulge mass and black hole mass. Larger bulges host larger black holes. The Milky Way's modest black hole mass is consistent with its overall scale and its relatively gentle feedback history. Our galaxy has never been a powerful quasar. It has not dramatically reshaped itself through black hole-driven outflows. UGC 12,591 may have experienced stronger black hole activity in its past, contributing to early regulation of star formation. These contrasts emphasize that galaxies do not simply scale up or down uniformly. Different components respond differently to mass, environment, and time. Halo growth, disk formation, star formation, and black hole feedback all interact. What does this mean for our own future? The Milky Way is expected to merge with Andromeda in several billion years. That event will dramatically alter its structure, likely producing an elliptical galaxy. In that sense, our galaxy's future includes a major merger that UGC 12,591 appears to have avoided, at least so far. UGC 12,591's environment may be such that it will continue evolving quietly, maintaining its disk for a long time. Or it may eventually experience mergers that transform it. We do not yet know. But the comparison reminds us that galaxies have lifetimes measured in tens of billions of years, and their present appearance is a snapshot, not a final state. There is also a more subtle implication regarding habitability in cosmic context. The Milky Way's moderate mass and rotation speed may be favourable for long-term stability of planetary systems. Extremely high rotation speeds and dense environments can increase radiation exposure and gravitational perturbations. UGC 12,591 scale suggests a much more energetic environment, particularly in its inner regions. Whether such environments are more or less conducive to life is an open question, but it highlights that not all spiral galaxies provide similar conditions. Living in the Milky Way is not merely a matter of location. It is a consequence of the galaxy's specific evolutionary path. Another lesson from this comparison involves perspective. When we study galaxies, it is easy to anchor intuition to what we know best. The Milky Way becomes a template. UGC 12,591 challenges that anchoring. It shows that spiral galaxies can exist at scales far beyond our local experience. It demonstrates that our galaxy is not near the upper bound of what spirals can be. It occupies a comfortable middle range. That middle range may actually be advantageous. Extremes often come with trade-offs. UGC 12,591's extreme mass and rotation push against cooling limits, stability thresholds, and rarity. The Milky Way avoids those pressures. From a cosmological standpoint, the existence of UGC 12,591 does not diminish the significance of the Milky Way. It contextualizes it. It places our galaxy within a spectrum of outcomes shaped by dark matter, gravity, and time. It also reinforces the universality of the underlying physics. The same laws govern both systems. The differences arise from initial conditions and subsequent evolution, not from different rules. That universality is comforting. It means that understanding extreme galaxies helps us understand ordinary ones better. The Milky Way's rotation curve, its halo mass, its disk thickness, its star formation rate, all make more sense when contrasted with systems at the edge of the distribution. Extremes clarify norms. In practical terms, studying galaxies like UGC 12,591 helps refine estimates of halo mass distributions, angular momentum ranges, and stability criteria. Those refinements feed back into models used to interpret observations of the Milky Way itself. For example, understanding how massive halos influence disk thickness helps interpret the vertical structure of our own disk. Understanding how early halo formation affects star formation histories informs studies of the Milky Way's stellar populations. In this way, UGC 12,591 is not distant in relevance, despite its distance in space. As we draw lessons from this comparison, one final perspective begins to take shape. Our galaxy is neither extraordinary nor insignificant. It is one outcome among many, shaped by dark matter and gravity in a universe that allows for far more variation than we once imagined. Recognizing that variation does not make our place smaller, it makes it clearer. After examining extremes, comparisons, and limits, the remaining question is not about speed or mass, but about meaning. What does it feel like to exist in a universe capable of producing both quiet, familiar spirals and vast, fast-rotating giants? Somewhere between the smallest things we know and the largest things we can imagine, there is a quiet consistency to the universe. It is not obvious at first glance. Space looks empty. Stars look scattered. Galaxies appear as isolated islands separated by darkness. But when you follow the motion long enough, when you trace the paths carefully, a pattern emerges. Things hold together. UGC 12,591 is one of the clearest reminders of that fact. A galaxy spinning faster than any other known spiral, embedded in an invisible halo weighing trillions of times more than the Sun, existing calmly for billions of years without tearing itself apart, does not suggest chaos. It suggests balance. Not balance in the everyday sense of stillness, but balance through motion, through opposing forces locked into long-term agreement. Everything about this galaxy should make us uncomfortable if we expect simplicity. Its size stretches expectations. Its speed pushes intuition. Its reliance on unseen mass challenges our senses. And yet, it works. It persists. It obeys the same underlying rules as everything else. There is something quietly reassuring about that. When we look at UGC 12591, we're not seeing an exception to the universe's order. We're seeing an extreme expression of it. Gravity pulls inward. Motion pushes outward. Dark matter provides depth. Angular momentum provides structure. Over time, the system finds a configuration that can last. Nothing about that configuration required intention. Nothing was planned. It emerged. This is worth sitting with for a moment because it reframes how we think about complexity. A galaxy with 1 trillion stars does not require special rules. It requires time, matter, and gravity. Given enough of those ingredients, even the most elaborate structures arise naturally. That realization applies just as much to our own experience of the universe. We live inside a galaxy that is itself held together by forces we do not feel directly. The Milky Way's halo surrounds us invisibly. The sun moves through it. The Earth moves with the sun. At every moment, gravity quietly redirects motion that would otherwise drift away. We float, but not freely. We are bound. It is easy to think of space as empty, but emptiness is misleading. Space is structured. It has curvature. It has fields. It has gradients of mass and energy. The darkness between stars is not nothing. It is part of the system. UGC 12591 makes that explicit. Most of what matters in that galaxy cannot be seen. Most of what matters in the universe operates beyond direct perception. Yet its effects are consistent, measurable, and dependable. This does not diminish the value of what we can see. The stars still shine. The spiral arms still trace graceful arcs. Light still carries information across hundreds of millions of years to reach us. But it places light within a larger context. The universe is not built primarily from what glows. It is built from what pulls. Once that idea settles in, something subtle changes in how scale feels. The gap between us and distant galaxies remains vast, but the rules connecting us feel closer. The same gravitational principles that shape UGC 12591 shape the Milky Way. The same dark matter framework that stabilizes that distant spiral stabilizes our own. We are not spectators outside the system. We are participants within it. There is also a lesson here about limits. UGC 12591 sits near the edge of what spiral galaxies appear capable of becoming. Its mass, rotation, and structure approach thresholds beyond which disks tend to fail and ellipticals emerge. It exists at a boundary, not because the universe likes boundaries, but because stability has conditions. Boundaries are not walls. They are regions where outcomes change. The universe does not forbid larger structures. It simply channels them into different forms. Push mass too far, and disks give way to spheroids. Increase rotation without sufficient gravity, and systems dissolve. Balance is not guaranteed, but when it is achieved, it can last a very long time. That idea echoes at many scales. Stars balance gravity and pressure. Planets balance motion and attraction. Galaxies balance rotation and mass. Clusters balance expansion and collapse. Even the universe as a whole balances expansion against the pull of all that exists within it. Nothing is static. Everything is dynamic equilibrium. UGC 12591 is not frozen in time. Its stars age, its gas evolves, its halo continues to interact with the cosmic web. Over billions of years it will change. But for now, it occupies a stable configuration, one that has endured long enough for its light to reach us. That endurance matters. It tells us that the universe is not fragile. It can sustain complexity over enormous spans of time. Structures do not require constant maintenance. Once formed under the right conditions, they persist. This persistence is what allows galaxies to become homes to stars, stars to host planets, and planets to remain stable long enough for chemistry to become interesting. Without long-term balance, none of that would be possible. When we talk about living in a dark matter universe, or a gravity-governed cosmos, it can sound abstract. But the implications are tangible. The fact that galaxies hold together is the reason there are galaxies at all. The fact that galaxies hold together is the reason stars can orbit calmly rather than scatter. The fact that stars orbit calmly is the reason planetary systems can remain intact. UGC 12591 reminds us that even at the most extreme scales, this quiet reliability persists. There is also something humbling in recognizing how recently we have come to understand this. For most of human history, galaxies were unresolved smudges. Dark matter was unknown. Rotation curves had not been measured. The idea that most mass is invisible would have sounded implausible, and yet, the universe was already behaving exactly as it does now. Our understanding changed. The universe did not. That gap between behavior and comprehension is important. It suggests that reality does not wait for explanation. It unfolds according to its own logic, whether or not we are ready to describe it. UGC 12591 existed long before anyone measured its speed. It rotated long before anyone named dark matter. It maintained balance long before any model predicted it. We are late arrivals, learning to read patterns that were already there. There is no urgency in that realization, no disappointment, just perspective. The universe is patient. When you zoom out far enough, urgency fades. Billions of years become normal. Hundreds of millions of light years become manageable distances. Extreme speeds become steady motion. Even the idea of defying gravity dissolves under closer inspection. UGC 12591 does not defy gravity. It demonstrates gravity operating at full strength, supported by mass we are still learning to understand. This distinction matters because it shifts the tone from confrontation to coherence. The universe is not fighting itself. It is negotiating balances. That negotiation produces spirals, halos, filaments, and voids. It produces quiet giants and modest systems alike, and it produces continuity. Continuity is perhaps the most underappreciated feature of the cosmos. Despite expansion, despite entropy, despite constant change, structures persist, motion repeats, orbits continue, patterns endure. UGC 12591 is one of those enduring patterns. When we imagine floating in space, it is easy to picture isolation, a small object suspended in emptiness. But the reality is different. Floating does not mean disconnected. It means moving within a larger system that provides context and constraint. We float within gravity. We float within dark matter halos. We float within cosmic expansion. None of these are felt directly, but all of them shape our trajectory. The universe holds together not because it is rigid, but because it is relational. Everything is connected through force, influence, and history. That connection extends across time as well as space. The light from UGC 12591 began its journey toward Earth when early mammals were just beginning to diversify. It travelled through expanding space, through regions shaped by dark matter, through the gravitational fields of countless other structures until it reached our instruments. That light carries information, but it also carries continuity. It is a reminder that the universe does not reset itself. It accumulates. Every galaxy we see is a record of what came before. Every extreme system tells us not just what is possible now, but what was possible then. UGC 12591 tells us that early conditions allowed massive halos to form, that angular momentum could be retained, that disks could grow large without being destroyed. That balance could be achieved even under extreme circumstances. Those lessons feed forward into our understanding of everything else. They help explain why the Milky Way looks the way it does. They help explain why galaxies cluster the way they do. They help explain why structure exists at all, and they do so without drama. There is no cosmic struggle visible in the data, no sense that gravity is barely holding on. Instead, there is composure. The galaxy rotates, the halo supports it, and the system endures. That composure can be surprisingly comforting. In a universe often described as vast, cold, and indifferent, there is nevertheless reliability. Forces behave consistently. Structures persist. Even unseen components act predictably. This does not mean the universe cares in a personal sense, but it does mean it is not arbitrary. Understanding that does not require excitement. It requires attention. UGC 12,591 rewards attention, not because it is loud or violent, but because it is quietly extreme. It shows us how far the familiar rules can stretch without breaking. And once you have seen that stretch, the familiar begins to feel richer. The Milky Way's rotation becomes more meaningful when you know how much faster galaxies can spin. Its mass becomes more informative when you know how much heavier spirals can be. Its stability becomes more impressive when you understand the boundaries it sits within. Comparison deepens appreciation. As this exploration slows, there is no need to arrive at a final conclusion. The universe does not conclude, it continues. UGC 12,591 will continue rotating long after this moment passes. Its stars will age, its halo will persist, its light will keep travelling outward, reaching places we will never observe. The Milky Way will continue its own motion, the Sun will orbit, the Earth will rotate, night will come again. All of it held together by forces that operate quietly, reliably, and without announcement. If there is a final thought worth resting on, it is this. Even in a universe dominated by darkness we cannot see, structure emerges. Even at extremes that challenge intuition, balance is found. Even across distances that defy imagination, connection persists. We are not suspended in chaos. We are moving within a universe that, in its own vast and patient way, knows how to hold itself together. And with that understanding, there is nothing left to do but let the motion continue, unhurried, supported, and steady, as everything that exists carries on exactly where it belongs,